Oh yeah. Hey, hello and welcome to this August 27th edition of the SkyTour LiveStream, coming to you, as always, from the John Zach Memorial Observatory in picturesque northwestern Connecticut. Tonight, it's an exceptional night, except we have some clouds around. We'll try to work around them, and we're going to go see some emission nebula and try to get back to some reflection nebula. And we'll see them all tonight because it's the deep sky. Once again, the moon is up, as you can see on the screen, but these cool clouds passing in front of it look really neat, and I thought I'd leave it there for a while. Hey, if you see anything you want to see in the sky, let us know. We'll try to find it for you. Until then, the telescope is almost temperature ready, and we'll get back in a moment. Good evening, everybody. Welcome to the SkyTour LiveStream for this evening, August 27th. It feels like December to me here. It is chilly. I'm wearing a couple of sweatshirts, and I have a hat and gloves standing by because I usually will need them on these late August nights. Anyway, I thought I'd start tonight with the moon. Why? Well, because it's got something interesting going on it. If you look at it on the screen, you can see that the moon, all right, I'm just going to move the dark side so we can see it. That is the unlit side of the moon. Now the moon is waxing, which means it's getting larger in this cycle. And as it's growing in size, we notice something interesting. We notice that the unlit side actually has a glow that you can see. Now, let me just use the camera to illustrate that a little better. If I actually do, let's see, let me do this. If I increase the ASA, that is the ISO, you can see the dark side, that is the unlit side. And as the cycle continues, because the moon's face that we see, even on this unlit side, is always facing us, that part of the moon will become lit over time, obviously. Now, this is caused by the light of the Earth reflecting on the moon. It's called Earth shine. And it's something that early peoples really didn't have any idea about. But you could see in a nice clear night, if you look up at the moon, you can actually see that the moon was a ball lit with a shadow that is curved, just like a shadow on a ball. And that's what we see here. We see this very thing. Now, if I move over a little bit, we'll actually see that and we bring the lit side in, you can actually see that curved shadow. I mean, you can actually tell that that's a round ball being illuminated far out on the right by something bright. And of course, that's obviously the sun. But it's cool to watch these things and learn them. When I was a little kid, when I looked at the moon, the way we all saw the moon in the telescope, well, it was kind of like what you're about to see. All right, it was kind of like this here, where, okay, let me just bring it down. Sorry, I had the wrong setting there, 1 second. It was like this, where the moon would actually look like this in the telescope. And we were used to seeing this. And that's wonderful, but that doesn't tell the whole story. The whole story gets told when you actually start to look at overexposures of the moon, and then you see over to the right. And I only move the moon to the right so that we can actually see that shadow better. Okay, so now it's actually a little more clear, right? And so then I always wonder, oh, what's that? I'm actually seeing the dark side of the moon? Of course, there's a little kid talking now, and I said, wait a minute, that can't be the dark side of the moon, because the moon is always facing us. It always has the same face facing us. And that's how I discovered at an early age, without being taught, I discovered how phases work. Because I had a ball, a regular ball, a play ball. And I looked at it in the sunlight. And when I moved my head around it, I saw that the shadow would go from being straight on, like when the moon is, when it's half lit, from directly from the right or the left. And then if I moved my head, the shadow would be curved as it follows the contour of the ball. And I thought, wow, that's kind of like the moon. And then as a little kid, I couldn't put it together any farther than that, but I just decided that that had to be how the moon worked, that it had to be this ball being lit in space. Now, we knew that, when as a little kid, until you're told, you don't really know what the moon is. You just see it's a thing in the sky, you hear about it. However, when I looked at it, I had this innate feeling that it was round, a sphere. Because I saw the shadow and I knew how it operated on my play ball, okay? And so that's why I figured that that had to be the moon, and what the moon was all about. So that said, I thought it was pretty cool, and I wanted to actually, have this there for you to see as well, because most of you, if not all, in fact, hopefully every single one of you, understands that the moon is, not flat like these flat tards. Oh, did I say that? Oh, I think I did. Would have you believe. And speaking of the flat Earth, I received a message from a guy who read my article on the Huffington Post, and he said, "I read your article on the flat Earth, and I was absolutely disgusted." And I said, I have to read what he has to say, because I couldn't wait to see what he had to say. And he was disgusted with me. He called me all kinds of names, of course, because that's what they do when they have nothing else that they got. And he said, I'll debate you anytime, even on my site. Well, wait, why don't you debate me on my site? So I wrote him back, and I said, look, I'll debate you anytime, any place, but I just need you to answer one question. And then I gave him just one of the things in my article that clearly they can't answer. And that was, if the sun is just approaching us from a flat Earth, we would never see the sun disappear under the horizon or, at all. But clearly it does. So how does that happen on a flat planet? All right. And I said, while you're at it, how come the angular size, it is the diameter of the sun in the sky, doesn't change all day and into the evening? How could that be? And if it's only a few thousand miles away, as you say, then this change would be radical and even more pronounced. So tell me how that works. And I said, when you can get back to me with those, we'll have a debate. Amanda, are you there?
I'm here.
What do you think?
I had nothing to do with this.
No, but what do you think the guy said to me? When I made those comments, how do you think he responded?
I would assume that you didn't hear back yet.
Exactly right. I never heard from him again. And
yeah, when you said what's the response, I was like, you got a response? Seriously? Yeah. I figured it would be crickets.
Yeah, it was definitely crickets. Oh, okay. There's another cloud about to pass in front of the moon, so you're gonna see it, and it's gonna look really pretty. And that's why I've got the moon off to the side like this, just kind of give it a little bit of a appeal. Yeah.
Speaking of things on the stream, I was just posting the link on my Facebook, and I tweeted a few people. Nice. And then when I came back, you still have the stuff from the burn the other night on the screen. Can you hop onto OBS and take that off for a second?
What do you mean?
Just
what do you mean it's on?
The writing that you had from the other stream. I mean, the title, we can change the title, but it's actually on the screen.
I'm looking right at it, and I'm not even thinking, oh wow. Terribly sorry.
No, just because when we go to look at Nebula and stuff, we want to see the pretty colors and or whatever we're looking at tonight, You
don't want to see this. That's what you don't want to see. I get it.
Yeah.
Oops, I did.
And I feel bad, because I did, because you were going to change the date, and I don't even see the date here. I just saw the title was Do Heater Test, which I figured, well, we'll just deal with it later. Don't worry about it. No, and then I saw it on the screen. I'm like, but I didn't want to interrupt, so.
Yeah, no, I'm going to be doing that. I'm sorry, guys.
That's okay.
It's my fault. Yep. I have to change it. I see, from the inside the dome, it's kind of hard to do that.
I know, when you're in the dark, too.
Because I'm in the dark, yeah. And
Yeah.
I also, I don't know if you noticed, but every now and then I'll when I go to move in the dome, you'll hear this loud noise. That's me kicking the stool that's in here that's on wheels. And then it goes sailing across the floor, and when it goes sailing across the floor, it ends up causing a distinct noise that sounds like wheels going across uneven flooring, and that's because I have these little round circles that are part of the floor tiles that are rubber, and so whenever you roll across the floor, it goes brrrr, and that's what you were hearing. So it's not in here right now. I'll probably need it later. So that's something. And you know what? For those that are just sick of seeing this without seeing the moon, let me just bring the moon in for you, because I'm kind of being sort of crazy here and not giving you the moon that you may wish to see. So there it is, looking pretty. And we will, like I said, we'll come back to it. But see, we're just shy of first quarter. And what does first quarter mean? First quarter means it's first quarter of the way around its orbit around the Earth. So when we see that as first quarter, it means it's going to be beside the Earth, and basically at the same distance from the sun as the Earth is, which means it's directly beside us. And so the shadow
starts waning.
Well, it's still waxing at that point.
Oh,
all right.
waxing. Okay.
And it's going to look like it's half lit. That's what people would call a half moon, half lit up. But in fact, the moon is always half lit. We know that intellectually. And then that's the waxing side, and as it moves farther along in its orbit, past that first quarter of the way around the Earth, you see the shadow start to go the other way in its curvature. Right now it's curved a little to the right. When it's at first quarter, you won't see any curvature in that shadow because it's directly beside us, so to speak. And then as it goes a little farther in its orbit, that shadow curves to the left.
Oh yeah, that makes sense.
And then it goes more and more and more until it's full, when you don't see that anymore. Then as it goes, that's what's funny is that's the half. It's a quarter. First quarter is the point where it's directly beside us. Half rotation, half revolution around the Earth is where it's full. And so if you said, okay, it's half moon, therefore it's full, I mean, I think people's heads would explode. So that's why they say full moon and just leave it at that. They don't say anything else. But then as it continues around, then that shadow is now going and leaning to the right again. But it's just shy of a full moon, and now it's going to go less and less until again it's on last quarter, where again it's beside us, but on the opposite side of the Earth. Therefore, it will be, again, a straight up and down terminator, that is a division between light and dark on the moon. And then that's last quarter. And now the remaining quarter is going to be less and less of that quarter lit up, that last quarter view. And the shadow is going to go more and more toward the crescent phase, and that's called the waning crescent phase when it's at that point. And then it becomes new moon. So it's pretty cool. It's interesting how this works, and I really enjoy this talking about it, because I tell you, I never get tired of telling people, how the orbital mechanics works, because orbital mechanics is exactly the kind of thing that, even at a rudimentary level, like I try to share with you, this is the kind of thing that we need to understand if we're going to, understand the universe. It starts with simple orbital mechanics. Understanding how these spheres go around each other. Now, the moon has mass, and thus gravity, and therefore the moon will also tug on the Earth. We know that it does because we have tides that are caused by the moon. Tides are also caused by the sun. To a lesser extent, the sun is 400 times further away than the moon is. And what's interesting about that is the tides created by the moon pull our Earth, but the entire Earth is being tugged by the moon as well. So if you saw these, both the Earth and the moon from above, and you weren't centered over the Earth or the moon, you were just sort of like at a neutral point in space and following the pair of them as they go around the sun, you would actually see the moon goes around the Earth, but you'd also see that the Earth makes a little bit of a circle too, meaning it doesn't stay perfectly in place. It actually is orbiting the moon as well. But its orbit is very, very, very tiny. It's actually a small amount. It's called barycentric motion. For instance, if you pick up a little kid and you swing them around by their arms, the Department of Children and Families will come and take you away nowadays because you're not allowed to do that anymore. But in lieu of that, if you were to pick up a little kid and swing them around by their hands, and they're laughing and enjoying it, if you stayed perfectly upright when you did that, then you'd lean into them and fall over because their mass would pull you over. So what do? You lean back a little bit as you spin them around. So now, neither you nor the kid is, rotating in a fixed position. You're not in a fixed position, just rotating around on your axis. You're leaning back. So the center of rotation between the two of you is not inside of you. It's sort of about maybe a foot and a half outside of you to the front toward the kid, because you have to lean back a little bit. So that's what the Earth is doing, basically. The Earth has to do the same thing, and so that's called barycentric motion. So the Earth and Moon do that dance, and the Sun does it too, with all the planets circling it. In fact, in one of my lectures, I talk about planets around other stars, or exoplanets, and I go through that. I talk about how over the decades, astronomers have mapped the location of the Earth, of the Sun, and figured out how it moves due to all the gravitational tugs from all the planets in our solar system. And when you see the path, it's a strange looking path. It's there are little circles, and they're strange circles. Sometimes the planets are near each other, and so the circles are a little bigger on one side versus another as it's moving around. You'd have to see it. It's crazy, but they have data from like back in the early 1800s all the way until recently. And you can actually see how the Sun actually moves. The Sun, 864,000 miles across, the most massive object within 4 light years of us. And that Sun is also being tugged and pulled by the planets. So gravity does work a lot on every single body in the solar system. And nothing is sitting still. And I think the hardest concept for people who think the Earth is flat versus round to understand is that the Earth is rotating on its axis at just over 1,000 miles an hour. And then I've had this debate where someone, and I just talk facts. If they can't handle the facts, well, then I'm out. But they basically said, well, if the Earth is rotating at 1,000 miles an hour, then how come the moon shadow on the Earth goes from west to east? Shouldn't it be going from east to west? Think about that. Okay? If the moon is orbiting the Earth 240,000 miles out, shouldn't it be traversing the Earth slower than the Earth is rotating? After all, we're on the Earth. Shouldn't it be moving very fast? Right, it is. It's moving just over 1,000 miles an hour. Well, the truth is, and again, it just comes down to science. The truth is that, and I gave all the clues, the moon is 240,000 miles away. And the Earth is moving 1,000 miles an hour. But, okay, the moon is also moving in its orbit at, it's actually 1.2 kilometers per second. You can convert that to miles an hour if you want. But coupled with the rotation of the Earth and the speed that the moon orbits at that distance, it's just lagging behind it's just ahead of the rotation of the Earth by just enough so that it actually overtakes the rotation of the Earth as it moves around, just slightly. And that's why the shadow drifts lazily for hours across the United States from west to east. And, you know, that's one of those facts of astronomy that you learn based on that thing I talked about a little while ago, orbital mechanics. La la. And that's the cool thing. Now, I don't venture to say that everybody understood that, but I'm happy to take questions if you have any questions about it, because you know, this is the truth, and this is the science in operation. And looking at the moon the way it is, you say, well, wait, you know, so everybody's moving that fast, how come the moon's just not, you know, racing across the sky if we're moving 1,000 miles an hour? Because at the speed the moon is moving, you also notice, don't you, that the moon goes from the west to the east in its nightly ritual, doesn't it? That's proof that it's actually overtaking the rotation of the Earth. Okay? You can actually gauge the distance of the moon, or sorry, gauge the position of the moon at 8 o'clock in the evening. And by midnight, you will see that it has actually traveled eastward a little bit. And that's something that, you know, is proof of what I'm saying. The people that, and again, I responded to a YouTube video. I don't know why I do this, folks. I think maybe because I'm crazy. A guy used the fact that the moon goes from west to east, you know, on the in the eclipse path, to argue that the Earth is really flat. And I don't know how he got to this convoluted reasoning. I think he was trying to say that NASA was lying and all that. It's always NASA. Why is NASA lying? Wasn't Copernicus lying? How about Galileo? Was he lying? Galileo was hundreds of years before NASA. So I don't understand. I guess all these scientists are lying and just keeping the secret that they don't even realize they're keeping or something. I don't know. Well, anyway, go ahead.
I think it's because the flat earthers believe that NASA lied about us landing on the moon. Either we didn't do it at all, or we did it much later, and the stuff they showed us was all fake. And based on that, they can't trust anything that NASA says, and they say because of not panoramic. I forget, when you take pictures of the Earth in space,
yeah,
all the pictures have to be edited together so you can see the full curve. But since it's not one real picture showing the curve, therefore we don't have any proof.
Well,
that's what the argument is. So all your facts are based on stats that came from NASA, which you can't trust, right? So it just goes around in a circle, and
the thing that destroys
it would be a great conspiracy to be behind, though, if it was true.
If it was real, yeah.
But it's crazy.
But it's crazy. Yeah. The silly thing about all that is that the obvious proof is just go look up, the high definition Earth viewing experiment, HDEV, online, and look at the live view. I mean, you can go watch the live stream right now, in fact, and see the view from the ISS, the International Space Station. And you have to say, they say, well, they use lenses that they curve the field. Oh, okay, but I mean, those lenses don't curve the Soyuz spacecraft that you see in the same picture docked, and they would. So the only resolution to this dilemma that they have is to say that it's all fake. It's all computer generated. Oh, but then there's that little problem of you can calculate where the ISS is going to rise and set in your locality, and then look up and see it. And it fades into view and then fades out of view as it crosses the Earth's shadow and goes behind into the dark. And that's...
See, but I don't know. If I was a flat earther, rather than say, oh, the ISS curves the camera and blah, 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 I'd say, like, it's probably just a studio in Hollywood.
No, but
that would make it a lot easier, for argument's sake, you know?
Right, but like I said, how do you argue with the fact that you can then look at any satellite up in the sky? I mean, how do satellites work in the flat Earth realm? They don't. It doesn't orbit. So how is it that they are repeatedly visible? And then they have to resort to these other ludicrous theories about, well, the Earth is really actually it's not like you think. It's a strange. It's a dome. Yeah. We're looking through it at a dome. Yeah. Oh, okay. Dome. I see. Okay. Well then, how does that explain the comet we all viewed in our SkyTour LiveStream a few months ago, where we came back a couple hours later and we actually took images of the same comet? And guess what? The comet was in a different place. How does that happen on your dome theory? I mean, are they changing the projection on the dome? Is it like, is there a Wizard of Oz somewhere? Don't look at the man behind the curtain running the earth. You know, it gets more ludicrous and more ludicrous as you go. And I gotta tell you folks, I'm never exhausted talking to the flat earthers. Okay.
I don't know how that can be true.
Well, here's the thing. There was a show I did a few years ago, which Amanda knows well, because she's the one that scheduled me for it. Now, this is before I even knew Amanda. And she told me...
And I did not trick you.
I'm going to tell you...
And it was not...
Stop defending yourself. I'm going to be fair. She probably, to her credit, told me that it was a flat earth debate. For whatever reason, I didn't fully understand that. And I actually was flying. I know why I didn't. I was in the middle of preparing to fly to Los Angeles from Connecticut because I had to speak at the Mutual UFO Network Symposium out there. And so when I got there, I got the reminder, oh, I got to be on this show. I called in, completely forgot about the topic. And then I had no time to prepare, and this other guy, who I will not name, and neither will you, was sitting there probably with his page of notes in his mother's basement, okay, you know, snibbling away and laughing in hideous glee. He's going to get this science guy. And he started rattling through all these facts that he had invented and concocted. And it turned out that, like, the biggest thing he had was, well, we don't actually have a picture of the curved Earth. And I was like, well, of course we do. And then anytime you named the pictures of the curved Earth, he said, well, that's fake. Well, okay. So, any of my data that I give you is going to be fake. And you're going to say it's just fake, and that's how you rationalize this? You know? So finally, I resorted to, and I wasn't actually in the room with Nick Pope, Lee Spiegel, and a number of other speakers, actually. And we were sitting in this hospitality suite. And they were very kind to say, oh, it's okay, you can stay here while you're on the radio show. We'll just listen. So I put it on speakerphone. And when they went to commercial, Nick Pope told me a joke that he said I should play on these guys. Because he recognized that I just wasn't going to have any of this flat earth stuff. And, of course, he doesn't either. So when they came back, I tried it. And it didn't work because they didn't really get it. And that's okay. But basically, what I said was, you know, there's a place in Russia where, where the Earth really is flat. You can actually see that it's a flat Earth, and it's a place called Lake Uranut. And they said, Lake Uranut? I said, yeah, Lake Uranut. And they said, huh, Lake Uranut? I said, yeah, you're a nut. And I just let that ride. And you know, I thought I'd get a better reaction. I mean, everybody in the hospitality suite had to mute it because everybody was laughing so hard. And as I look back on it, you know, that probably wasn't the best way to handle that because, you know, I ended up, antagonizing them and all that stuff. And you know, I really didn't serve the debate purpose very well. And I grant you, I agree with that. So, in intervening years, I've assembled a bulletproof argument for the spherical Earth. It's kind of easy, really. I mean, it's sort of like shooting fish in a barrel. It's low-hanging fruit. But not to these folks. So I don't understand why they're like this, but it's what it is. Now, I think I've had enough of the moon. And what I would like to do is I want to take us to something else, if that's all right. If there's any requests, you go right ahead and bring them up. And I'll be happy to ignore them. No. And I'll certainly entertain them. I'm going to go to one other thing right now because we're going to lose it soon to the season. And I would just like to, I'd like to see it and have us look at it another time. So, see, Amanda, I was being kind, and I certainly don't blame you. All the blame's on me. I was the one that kind of lost it and went, crazy on these guys myself. That was me, not you.
Wow.
All right, I'm moving the scope now.
Now, well, you know, I didn't want to do that show in the first place. It was so stressful. I just thought the flat earthers, I mean, when I put word out that this is what we were doing,
Yeah.
people could not respond fast enough. Oh, who do you got? What astronomers can I take on? You know, can my friend come? Because it was going to be it wasn't even an easy email to write, because I'm like, okay, I'm trying to get two, like, proper astronomers, scientists that are smart enough to, you know, explain how, you know, rotation and revolution and orbits and blah blah blah, and we're not flat, but good humored enough to actually waste 2 hours of their life talking to people whose opinions you're not going to change because it's their thing. You know what I mean?
I do.
And luckily, you know, you took pity on me. You were really nice about it until you got to the show, and then, yeah, bad things happened. And you say, you know, now you say it's no big deal, but I mean, then that was like 2 years ago, and, you know, Bill, our friend Bill, Bill NY Skywatcher, check him out on YouTube. He had some people on, and one of them was the head video and photo analyst for MUFON, and talking to a few other guys about, you know, different sightings and different pictures and blah blah blah, and then said, oh yeah, I'm actually an astronomer, you know, I have my degree in astronomy. And I'm like, wait a second, hold on, let's talk astronomy. And then you mentioned, I remember years ago, someone invited me on the show, and it was to debate flat earth, and I was totally blindsided and blah blah blah. And I said to Bill, I'm like, oh my god, what are the what are the chances that he was in a debate, like 1-on-1, 2 on each side? I'm like, it's just too similar. And he's like, no, don't worry about it, there's no way. I'm like, I don't know. And I went back to the show, and I said to the guy that owned the station, I'm like, do you have a list from 2 years ago for that date, for that flat earth debate? And sure enough, one of the guests was Mark D'Antonio, and I'm like, oh my god. And I checked the emails, I'm like, no. I explained that so clearly as best I could. It was flat earth, you were taking on flat earthers, and this is what it was. And I felt so bad, and look, he still talks to me. So,
well, that's because I actually don't have a you know, an agenda or a grudge. You know, I know exactly what you were facing. I knew exactly what you were trying to do.
It was a really successful show, though. Well, people listening absolutely loved it.
Yeah, they loved watching me get bashed in. You know, that was actually, you know, every comment on the video that's on YouTube now, very rightly was slamming me because I wasn't prepared. I didn't even make a single preparation because I didn't remember, because I had to do my talk at the MUFON conference.
I know. Feel bad now.
So, but that's okay. You know what? This is, and I'm not afraid to say it. I'm not afraid to say that. Yeah, I messed that up. That's me, on me. I totally get it, and I'm okay. That, you know, I'm okay now.
And now you've taken on your lifelong goal to destroy them.
No, I haven't. I mean,
you know, 3 years later, writing Huffington Post articles and doing A-Hole Astronomy with Keith, and
which we haven't done yet, actually. So I mean,
yeah, I don't know what happened with that. Yeah. Well, there's only so much you can say. I mean, there's only so many facts you can put in a video saying, guys, it's not flat.
That's right. That's right. But still, you know, the truth is that I'm not angry with the people that were, you know, coming after me with a vengeance like that. That's okay. That's them. That's what they do. You know, they have a belief system. I'd rather see someone stick to something they believe than be wishy-washy depending on who they're talking to. And those guys believe what they believe. And it's wrong. It's wrong. Intellectually and in reality, it's wrong. Completely dead wrong. But still, at least their conviction is there. They're convicted that this is the truth. And you know, I'd rather debate someone like that than debate someone who might say, yeah, I think you're right, and then behind my back say, yeah, he was wrong, you know? So, I mean, I've never changed my position. You know, of course, it's an easy one, right? It's low-hanging fruit. Earth is round. Hey, guess what? The rest of the science world agrees with you. Only like 400 people in the United States disagree.
Well, see, I mean, I remember years ago I heard Art Bell do an interview. It was a debate with Stan, a flat earther, and it was one of the funniest things I heard, because the poor scientist, he's like, I don't know. I don't know what else I can say, you know, and it just...
Yeah,
I thought it was really funny, but then now, looking back, I'm like, that's just a notch in that flat earther's debate saying, oh, you'll never guess what famous astronomer I debated. I mean, you know, he's still not proved his point, but it's a notch in his belt, right?
Yeah.
I feel bad for that anyway.
Well, that's okay, because frankly, it's almost better to let the ignorant run off thinking they won. Okay, because then, because if they didn't think they won, and if they would come after you with a vengeance, and they'd look for any opportunity to find some way to destroy you, even if they have to make something up, which they would. So I'd rather walk away from that, letting him feel vindicated, frankly. See, it's the what's the word here? It's a statistical retreat. You know, it's a methodical reasoning behind why you retreat from this. But as far as it goes, and I mean, now that I'm actually learned and prepared, and that is to say, research the proper reasonings. Actually, you know what? For all my reasonings I wrote in that Huffington Post article, I didn't consult anything online. Not a single thing. I didn't open the browser. I didn't do anything. I just sat there with my iPhone, and I went through my notebooks, my notepad in iPhone, and I just wrote down things that I knew were the right thing. And that ended up being the whole article. I didn't say anything, didn't consult anybody, didn't talk to anybody, didn't look up anything online at all, didn't look up counter arguments to flat Earth anywhere. I just did it all from my head, because I figured if I can do it out of my head, then I won't ever be caught off guard again. Because if it came out of my head once, it'll come out of my head again twice. I don't have to remember anything except just synthesize an answer again. And hey, guess what? It was the same answer. Oh, wow. Big surprise. And that's the thing, you know? I think that's cool, but... Anyway. I know, I kind of harped on this a little longer than I probably should have. But we are looking, by the way...
No, but it was funny, because I always said I would love to be friends with an astronomer that could explain things to me and would actually put up with all my questions and, you know, be willing to not just know an astronomer, but like actually be friends with one to get this kind of information. And
we exist.
It's like I had your email, I had your cell number like 2 years ago, and then I was talking to you a few times on Bill's stream.
Yeah.
Knowing, like, I don't know, just knowing you were a MUFON guy, and I don't really know anything about MUFON, nothing to add. I was just listening to the stories.
Yeah. And
then when in astronomy, I was like, wait a second, hold on. I've wasted a lot of time here when I could be picking your brain, and now you can't get rid of me. It's like feeding a stray cat.
Oh, you're funny. You know the group, the Stray Cats? With Brian Setzer?
Pardon me?
Do you know the group, the Stray Cats? Brian Setzer was the lead guy. He was a guitar player. You ever heard of the Stray Cats?
Do Stray Cat Strut?
Yeah, you know Stray Cats.
Did he do Stray Cat Strut?
Well, look it up. I don't know. I don't have access to my browser right now. But my great uncle was a guy who lived in Manhattan, and he's the one that taught Brian Setzer how to play guitar, as it turned out. Which I thought was really funny. And then my great uncle was Remigius D'Antonio. Yeah, back when people named their kids Remigius, and he was known as Remy. And Remy actually was the guy who, here's the truth. He was a guy who made it possible for anyone who didn't signal for a turn to get a ticket and a citation in the United States. Actually, around the world. Because he invented signal lights for cars. So,
wow.
My great-great-uncle Remy is the reason...
That's so weird.
I've even gotten the ticket for not signaling and making an improper lane change and stuff like that. Yeah. So, but that's a non sequitur. It has nothing to do with anything, and we have a blank screen right now, and I apologize for that, but really, what I'm doing here is I'm trying to see what's going on. Oh, I'm sorry. I was on I was on 4K video because I've got the
I was gonna say there's some buffer.
There is?
There's some buffering, and yeah. That our talking was getting a little distorted there. But yeah, just
Okay.
in chat.
Yeah, I'm in full screen mode. Oh, I'm doing 4,500 kilobits per second, so that's not bad. Frame rate of 30 frames per second. And I have 3 out of 4 Wi-Fi's, so Wi-Fi bands, I'm okay. For now. Of course that'll change. Give me a minute. But, now that I got us here, just want to remind you, actually, this is the Messier 13 globular cluster in Hercules. And if I come out of 4K video and just go back to that frame that I shot just a bit earlier, okay, not that one, that's this guy. Okay, you actually see this globular cluster in all its glory. This guy has several 100,000 stars, and it's literally, it's hard to believe this, but it's 23,000 light years away. I've talked about it before. And sooner or later, some of you in chat are going to say, "Oh, that's the one 23,000 light years away." I mean, they're all over 10,000 light years away, and most are over 15,000 light years away. Yet we're seeing the light from these stars, and so every one of the stars you see there, among almost every one of these stars, are among the oldest in the galaxy because they're called population 2 stars. They're the original stars that formed when the galaxy first formed, and many of the stars in the disk of the galaxy can be population 2 stars as well. But there's also a greater chance that the stars that are in the disk of the galaxy could have been affected by other activities like other supernova and so forth around them. And globular clusters are not immune to that at all. However, they all have a fairly uniform structure and fairly uniform makeup. That is, hydrogen and helium pretty much, not much else. So, as I mentioned to you before, these things orbit the galaxy. Like planets orbit the sun, these orbit the galaxy. And they're not necessarily orbiting on the disk, like we orbit on the plane of our, it's called the ecliptic, the plane of the ecliptic, which is the horizontal plane of our solar system. These globular clusters don't orbit that way necessarily. They actually are in a spherical halo around the galaxy, and they're orbiting every which way around the galaxy. And it's really an interesting set of mechanics to try and figure out how those orbits could get established. And it's really, really hard, especially considering that the stars within the galaxy are also orbiting the galaxy in the plane of the galaxy. So how these things happen to come about is really an odd thing. And there's people that study globular clusters and nothing else, and because they're so strange and intriguing. But so, you know, when we look at something like this, it is relatively nearby, okay? Now, M22, we saw before, that's in Sagittarius. That one is, I think, a little closer, and so it looks a lot bigger. And it's got several 100,000 stars as well. So it's really something. You know, this might have, like, say, the M13 here, Messier 13, might have around 250,000 stars or so. So it actually is pretty interesting. Now, you might say, well, if it's one of the oldest stars in the these are all the oldest stars in the galaxy, then how old is that? Well, it looks like these might be somewhere in the range, age-wise, to be about 12 billion years. Now, the universe is 13.8 billion years. So these clusters, this cluster is about 12 billion years old. So that's almost as old as the Milky Way. Notice I said almost. What this means is these particular stars, okay, formed before the galaxy had formed a number of its own stars, and thus these stars formed without the benefit of the other supernovae that spew, as we know, the periodic table elements off into interstellar space. So that's why they don't have a lot of those, what they call metals, you know, anything other than hydrogen and helium in them. But there are some that do. There are some stars within globulars that do. And I might have mentioned this the other night. I know I did, actually. And that is the reason they do is because of the fact that these stars, because they're orbiting through the disk of the galaxy, sometimes they'll punch right through the disk of the galaxy, come back up through the other side in their ongoing hundreds of millions of year orbit. And as they do that, they may dislodge and carry with them some of the stars that were in the galaxy. Maybe, we don't know, perhaps that's how globulars came about, is through repeated interactions with the galaxy disk as they went through. But by going through the disk at a time when there was very few stars, what they could do was pick up a lot of gas to actually form more stars. And most of that gas was hydrogen. So that could explain partially why these are all population 2 stars in globulars. They formed early on, before the Milky Way had a chance to really rejuvenate the periodic table by supernovae and so forth. So it's just a really cool cluster. I always like seeing it. I never get tired of it. So that's really neat. So I hope you didn't mind my little sidetrack to an object we've seen before.
No, we love it.
Well, you do, but who knows, you know? Let's see now. There's something else.
I think chat loves it too.
I hope so. I hope so. Let's see here. I want to see if
Yeah? Will Nebula... I don't know how to phrase it. I don't know. Okay, let me think of how to phrase it. Go to your next object. Check
okay. I'm going to head to the next object right now. So here we go. Okay.
I guess what kind of, I don't know, elements would it take to create a nebula? Or, like, will any ever form now? Or...
Will what?
Have they already been created and that's it?
Oh, no.
Nebula?
No. Star-forming regions... Okay, first of all, remember the Veil supernova remnant we saw?
Mm-hmm.
That's the supernova remnant in Cygnus with the beautiful arcs of colored, blue and red gas.
Mm-hmm. Yeah, I remember.
Okay, well, that's only a few tens of thousands of years old. So it's actually a supernova remnant that is relatively recent. And now that recent supernova remnant has actually obviously been here for a while, obviously for us, but to the rest of the universe, it's actually fairly young. And so as it moves through space, it's an expanding shockwave that's moving out at nearly the speed of light. That particular object, okay, all along the way, it's compressing other gas and dust that it finds along the way. And part of the visual supernova remnant that we see, okay, part of that visual supernova remnant we see is actually that compression wave, okay, the compression of this other gas that's along the shock front, that shock wave. Now, don't think of shock waves as only going through air. Shock waves also go through any medium that is a medium that is, less than, a little more than vacuum, and that's what we're talking about here. The medium being the interstellar medium, full of atoms. Now, the atoms may only be a few per square centimeter, or even a few per square meter out there. But with a massive object like a supernova remnant, it doesn't take much to compress those atoms along a shock front. And then those are caused to emit light by that process I told you about. They get ionized, that is, their electrons are forced off. They go to a higher energy state, and when they come back, they actually bounce back to a lower energy state, and they acquire an electron again, and when they bounce back, they give off energy. And depending on that transition, it happens at a certain wavelength, which corresponds to a certain color, and that's what happens. So that's what we see along the shock front. So those are new nebula that are being formed. And along that shock front, that compression could trigger star formation. So we've seen that before, where stars are formed along these shock fronts out there in space. And this is something that occurs in the interstellar medium, and it's ongoing. It hasn't stopped yet. It's still going on. Now, just to give you an idea, this object that we're looking at right now, this object is actually called the Iris Nebula. And if you notice, when we zoom in on this, this is a photo I just took. Hold on, here we go. We zoom in on this, you see that? This is the iris. Now the iris, you'll notice it has a distinctly different color than the other nebula. It doesn't look like the Lagoon Nebula, which looks reddish. It doesn't look like the Eagle, which is reddish. It doesn't look like the Omega, which is a purpley reddish. Okay, it looks blue. There's several kinds of nebulae out there. We see the nebulae that we associate with planetary nebulae, and these look like blue with fringes of red, like the Ring Nebula, and like the Dumbbell Nebula, like the Little Dumbbell, which is actually near this. We can go check that out too. Now, because our eye is not so sensitive, we don't see the color when we look through a telescope, but the camera can see the color. And so this, we're getting a color photo of the iris. Now, what is the iris? The iris is a location where that star in the middle is not quite hot enough to ionize the gas around it. So the dust that is around the star as well, okay, is being illuminated simply by the starlight. And so it's reflecting the light to us, and that's called a reflection nebula. Clearly, that means that the nebula itself, that stuff that's reflecting, is on the other side of the star from us, right? Because it has to be reflecting back at us. We wouldn't be able to really effectively see backlit stuff, okay? Like, you know, you put a light behind your hand. I mean, how can you see? You know, if you hold your palm towards your face and you put a bright light behind your hand, you're going to see basically a silhouette of your hand. You're not going to see the front with all the little lines in your palm and so forth because the light's too bright. In the same way, we got a star here. Now, we see this intricate construction of this nebula back there. How could we see that? The only way we could see it is if the star is illuminating it, reflecting it back to our eyes, so the light is actually going away from us, reflecting off the dust grains that are in the nebula, along with the gas, and then we see that as the reflection nebula. You'll also notice there's a little hint of red, don't you see it? A little bit below the star. It looks like it's a little bit on the purple side, okay? There is...
Of the actual star, or
no,
like in the
in
kind
the
of cloud kind of gas? Yeah.
Yeah, in the cloud you can actually see there's a little bit of reddish down below. Now, this is, again, the distance that this cloud is from the star is not really clear, all right? So when we see, now we can just say, you know, the distance is like, it's 1,400 light years, actually. Okay, when we think about the distance of the whole nebula. But the stuff that's reflecting to us, all right, is probably farther away where the ionization can't occur. It's not close enough to the star. But closer to the star, there might be some ionization, and that's responsible perhaps for some of the red. Although, we also know that we get a lot of dust in these nebulae, and we might see things called molecular clouds. And these are rudimentary molecules that are in the clouds that manage to combine, atoms that manage to combine in the cold of space, because there was really nothing there to disassociate them, not a very bright star with high energy or anything like that. So we see that as well. And that's, we're seeing molecular clouds, and right above the star, you actually see that little dark area. That's a molecular cloud, just sitting right up above the star. Yes, sirree. So it's a interesting, it's a very interesting little object, and I took a number of photos of it the other night, and I processed them, and sorry about that pop, poop, you know, and I processed them, so we're going to be able to see this on the SkyTour LiveStream site, so you'll see a little more detail in this nebula. So.
And I love the color.
Yeah, the color's beautiful. I'm going to go to 15 seconds. I'm going to come down to an ISO of 16,000, and I'm going to go to 20 seconds. So, no, I'm going to go to 25 seconds. Why? I'm a glutton for punishment. I just want to do this because I want to capture with a little less noise and a little bit more detail. And let's see what we get. Again, it's the Iris Nebula, and the Iris Nebula is known as NGC 7023. If Daryl was here, he would have spotted that off immediately.
He is here.
Oh, Daryl, come on, you're slacking. I'm kidding, of course.
He may have. I got a little behind in chat. I know.
Oh, then he probably did.
I think the cluster, I think he said was M13 or 12 or I forget. Yeah, something 13. Like that. He did mention that, but I don't know if he mentioned that. So this is an MSCR object.
No, this is an NGC object.
An NGC object.
Yeah. Now let's go take a look at this.
He says he's trying to behave.
He's alright. Alright, see now.
Well, no, because Jude showed up and then we all broke into a song and I got distracted and I'm trying to learn, so I'm trying to focus on what you're saying instead of chat.
No,
as cool. Much. I do have a few questions for you, but when you're ready.
Alright. So here we are again, and I wanted to take a picture to better show the dark cloud. You see it there now just above the star. I cut down the ISO, the sensitivity, and that means you're going to get less graininess to the image, but then I increased the exposure time, and now you actually can see a little better. Now I could go to 30 seconds and cut it down another stop or two, but you get the point. We see what we see here. The iris is actually a little gem buried amid some complex clouds within the galaxy. It's really cool. Now, as far as the size extends bigger than what you see here on the screen. It kind of goes about as far over as the left arrow, the left white arrow you see on the screen, and about as far over as the right arrow, and equally in both directions in the opposite direction, and maybe just a little bit more in all those extents. And that corresponds to about 6 light years across, right, at its 1,400 light year distance. So it's pretty cool, you know.
It's very cool. It's almost the color of Neptune. I think that's why you showed us the other night, because you knew I love those colors.
Yeah, yeah.
They're gorgeous.
Yep.
It's funny, actually. Well, not well. I think it's funny. When you showed us Neptune, and I was looking at the color in that show Sailor Moon that I love so much, there is a Sailor Scout that represents Neptune, and her hair is that color.
Oh wow!
It's like an aquamarine. And it is. Well, I think it looks more like Neptune than the iris, but it's beautiful. It's just like, I mean, I don't know.
That's really cool.
It's gorgeous. I love the color.
Yeah, it's a pretty color. I've always felt that these colors are just amazing, you know, and beautiful. Yep.
And that's just one star.
Mhm. Now I'm going to go to another object here that is not a nebula, but it is something interesting that I think you'll enjoy. And it's sort of nearby, not very far away. As you can hear, the telescope didn't even move very much. Gee, I wonder what object it is. Could it be the only object you can see on the screen? Why, yes, it can. You I really like these potpourri nights, okay, where I can get to show you some really cool things that are, different. I really like that.
Me too.
All right, so.
Well, it never has to be a night of only this or only that,
No,
right?
I agree. I'm just gonna.
Especially when you're open to taking requests.
Oh yeah, no, I like taking requests.
Hint, hint, chat. If anyone
Of
knows
course.
what's up and.
Yeah, what's up, chat? What's up? So, okay, this star that we're looking at here, a really neat star. This is the it has a special name because it's so it's throughout astronomy. People love this star. Okay, this is called the Garnet star, and it's actually an M2 supergiant. Okay, now M2 stars are what color, Amanda? Come on, M stars.
M stars.
Yep.
Oh, hold on.
Remember, from O, B, A, F, G, K, M, they're at the end of the scale.
It would be
Help her out, chat.
red.
Indeed.
Would it be red?
Yes.
Yay!
correct.
No, chat did not help me.
Are you sure?
I had 30 seconds. Yes, because in that little mnemonic, oh, be a fine guy, kiss me.
Mm-hmm.
M is at the end, which means they're cooler.
That's correct.
Whereas the O's would be hotter.
Yeah.
And in space, I guess hotter is blue and colder is red. And the stuff in the middle would be like a yellowy, kind of ambery, kind of in between, right? And because if you think about like a lighter or like a fire, like the really hot part at the bottom is blue. And then as it cools, relatively speaking, it's still hot, but then it goes orange.
Mm-hmm.
So, yes. And that's a good way of thinking about it too, right? That's all accurate, what I just said?
Almost.
Uh-oh, the middle part isn't yellow and amber. Is that where I went wrong?
The middle part is white, and then yellow, and then orange. Okay. So, you're close.
Okay, well, I'll take it.
And you're calling, yeah, okay, fair enough. So let's go back to this photo I just took. Okay, this is the star. Look at that color. Okay, this star is a K2 supergiant. It's called the Garnet star, and the star itself is it's actually a variable double star. It's actually a double star in its own right, and the stars that are the component that it's actually next to it, you can just barely see above it, and that corresponds to at the distance that the star is, it's 2,400 light years. That corresponds to 14,500 astronomical units, which is really cool. All right, and the star, like I said, is 2,400 light years away. And it's very luminous. It's extremely luminous. Now, it's actually called Mu Cephei, all right? It's actually known as Erakis. That's its name, E-R-A-K-I-S. And Herschel, astronomer Herschel, first found this star. And it was really neat because, to that point, of course, nobody really understood, what supergiants were versus giants versus regular stars. That was not until Ejnar Hertzsprung and Henry Norris Russell came up with the HR, or Hertzsprung-Russell diagram, which effectively showed the relationship between temperature and the star's color and luminosity. So there's all kinds of relationships that were built upon that base understanding of the color of a star versus its temperature. There's a mass luminosity relationship. There's a luminosity temperature relationship. So there's a number of relationships, and they all play against each other. And once you know a few elements about a star, you can figure out all the rest. And I love that. And on top of it, the star is a variable, and that's the case with most supergiants like this one. Okay, they are variable stars. What's that mean? It means that their brightness will vary. So tonight we're seeing it at whatever brightness it's at. I don't know what it is relative to its other brightnesses. I can't tell you because I don't have any photometric equipment to do a photometry study of the star here, so I can't tell you. I wanted to get a photometer, but there's so many. Gosh, I did a photometric study for my thesis, and I just there's so much to do. There's so many things you have to go through to just before you can start taking data. You got a lot of calibrations to do, and I'm patient, but I don't think I'm that patient anymore. I just want to be able to show people things and get to them. So this is what we call the garnet star. Now, here's something interesting. This star, probably within 1 million years, is going to be the next supernova that we'll see. Well, maybe not the next, but it will go supernova. It is a supergiant, and supergiants often go that route, and this one will be no different. And if you think about it, this star, this star is actually 15 astronomical units in diameter. Okay? Think about that. 15 astronomical units. That's big, isn't it? Considering that Neptune's 30 astronomical units away from the Sun. And, you know, it took us 15 years to go to Pluto, which was a little farther out. And here we're talking about a star that's, you know, over 1,420 times the size of our own Sun. That's incredible. So...
John's asking what the dim object to the lower right is. I'm not sure exactly what he's looking at. I mean, I see a few stars to the...
That's a field star. But the one we care about is the reddish, the little tiny red dot above the main star, the main star we see. That's actually the double star. Now, let's see if I can look at it dynamically here. 1 second. Just a second. Or did I just do something wrong? Hold on.
Uh-oh.
Yeah, no worries. I just did something wrong. I apologize. I'll get us back. Doesn't take anything to get us back, so it's not a problem. There we go. So you got us back. Okay. Okay, now let me hold on a sec.
I'm scared to talk because everyone in chat says I sound like a pirate. Not sure what that means.
Oh, I was the one talking like a pirate. You don't sound like a pirate. Oh, how come I'm at 0?
Thought it didn't,
for a second. Why am I at 0? What the hell? Then it jumps up again. I don't get this. I may have to...
I was going to say buffering, yeah.
Bill's going to come out Wednesday, and he's going to work on this with me. We're going to try and figure this thing out.
Oh, good. I know he offered. I'm glad that...
Yeah. Alright, so let me just go back for a minute, and I'm going to cut a little bit of the brightness. Okay, let's see what I got there. I got a really strange thing going on here. We still have the construction here, but this is now the 5th giant flatbed truck that's extra long, carrying these massive square objects on the back of them that's going up the street here. And oops, where'd it go? I don't know what it is, but I'm sure it's not good. What were you going to say, Amanda?
No, I was just cringing at all the trucks going by.
Yeah, it's like crazy. Can't wait till the construction's done, folks. Man. Oh, and by the way, I was looking at Arizona properties today, and talking to a guy in Arizona who was driving around to the different properties as I was talking to him. He came across a house in his town that he never saw before, and it has 2 astronomical observatory domes on the property. So I think I'm working and looking at the right area. No doubt about it.
That is a good sign.
It is a good sign. Because when someone puts that kind of money into this, trust me, I know, it's definitely a big deal. All right, so there's Herschel's garnet star, and you see the color pretty clearly. Now let me go. I want to move us to another location. Let me first. I had some clouds down south, so I couldn't really go to. I couldn't go out to Sagittarius. I still have them out there, so I can't. I can't look at the Eagle and then Lagoon or anything like that because there's clouds down there. Okay, so let's take a look at what we can see. By the way, the iris that we were looking at a few minutes ago, the iris was actually very near the North Pole. Not like so close that you can touch it, but I mean it was fairly close to the North Pole. And let me look and see what we got there. Okay, M101. All right. Well, let's try it. Okay, we're going to try and look at a galaxy called M101. I hope it's visible. Let's go. We're moving.
And some questions are coming in.
Okay.
This is kind of, I don't know. Well, one was kind of a comment, but I wanted to ask you about it, and then one was kind of a follow-up question, so I'm going to ask them both at once.
Okay.
Jay said that he watched that said, we have never seen a star being formed, only destroyed. And I was going to ask if that was true, because I thought I heard something about you've pinpointed where a star, I don't know, I thought it was going to be created in a few years, maybe like 10 years or something.
Well, we can't really put a time frame on the universe that way, but I gotta by the way, I'll try this one more exposure, but I don't think it's gonna work because the battery is low, and I've got another one in my hand, so. Okay, this is in sensitivity 4013 seconds. And we're gonna be looking at M101 if this exposure works. If it doesn't, we'll change the battery. No, we've actually been able to see a location where stars formed, and were there afterwards when they weren't there before. We've actually seen that. Some of these stars, these early stars, are called T Tauri stars, named after the star that actually looks that way, or sorry, named after the star of that designation. So, and we don't have anything on the screen here. Let me change the battery. So I'm turning off right now and taking out the battery. I have the old battery in my hand, putting in the new battery right now. Up in the camera it goes. Locked in. Camera back on. And let's see what we got. Okay, and this battery for some reason is at 41%, but don't worry, I have another that is fully charged. If we get to, there goes another big truck. They must be building a space station up here or something, I don't know. Okay. All right.
Be doing construction? I don't get it.
No, they aren't construction materials. I don't get what they are. But we'll see. Okay, I'll try this. It's 80,000 ISO for 25 seconds. Oh, actually, I do have a filter on there, and in that region of the sky, I don't really have a whole lot of sky glow, and I have the sky glow filter on. So we might get better luck if I take this filter off for this photo. And I may just do that. Only for this photo. Because it's in an area of the sky where we don't have to really worry too much. Okay, so now we're processing. Okay, 1 second, and it will come back.
Okay.
Yep.
Is the star being formed or destroyed? Yeah.
What's that?
You were saying about the stars being formed and destroyed? Could we see?
Well, we don't. I don't have one. I mean, we can't actually. I can't show you one. There's plenty of them in Orion.
No, but I mean,
The Orion Nebula
being
has several.
destroyed.
Oh well, that was.
Sorry, it seems like there's a delay or a problem on Skype now.
Okay. Well, the Vela supernova remnant is actually. Yeah. Okay. See, I can't see that, and I still have the moon up, so that's probably the reason.
And
but I am
just dropped.
What's that?
It just went offline and came back. It's buffering.
Yeah. Alright, I'm taking off the... I just shut off the camera for a second. And I'm going to just take off the filter section I have now. I'm going to put back on my straight through, where I don't have to worry about this. I may have to refocus though. I will have to refocus, but let's just take a look at what I got. Okay. Let's see what I got. If I can. Oh, good. I have stars that I can see. Okay, so now I just have to refocus for this other adapter, which I'm going to do. Great. So now I have this. Now let's see if I can catch the... This is... M101 has a very low surface brightness, so it's likely that it's not going to show up too well. But in order to find it, I should actually be able to... I don't think I've got clouds over there, do I? Oh, I do. Oh. Yeah. Okay. There's clouds over there. So I was trying to look at an area where there may be some clouds. But let me try and go to a different spot and see if I can see there. Oh, that might be open. Let me go to a different spot, different galaxy in that area. Try it out. Just a sec. I'm just going to move a little bit toward the west. Alright, here we go. Let's see what we get. Okay. Now let's do 15 seconds at 16,000 ASA just to check this out. This is very low to the horizon, by the way. I'm doing this in particular for one particular reason. I'm trying to see what the quality of the night is, and so I'm using a galaxy to try and figure that out. Because I'm only about 20 degrees above the horizon. Oh, I guess that's just a little too bright. Okay, let me drop that down. Oh, sorry, it wasn't 80. It was not. It was 120,000, not 20,000. My mistake. I'll do 25,600 for 15 seconds. Okay, that's better.
Yeah, I was just looking at chat and someone for Orion, and Daryl said, "Oh, it's not up until 3." So I said, "Is that 3 Mark's time?" And he said, "No, it's time." Are other things that consistent? Other things like at 4 in the morning, no matter where you are, you can see whatever?
Well, I mean, understand that the reasoning behind that is that when you let's just see, the moon is causing it to be bright. One of the things you have to consider is that we have to care about time zones, and the Earth rotates at a specific rate, just over 1,000 miles an hour. So it will show up at exactly the same place at exactly the same time. Okay, not the objects, but the Earth. Okay, it rotates at exactly the right speed. Okay, the same speed, very consistent, and there won't be any differences. So that said, we'll be able to see objects that are we'll be able to see objects that are rising, say in the wintertime. We'll be able to see them as they rise because we're waiting for them to come up. Why is that? Because the Earth's rotation is such that the Earth is going to be turning toward them. And at the particular location in our orbit, we actually see them at that point. Now, as the winter approaches, the Earth will be in the same position every year around the sun. And again, the change of the seasons has only to do with the fact that the Earth's on an axial tilt. Okay, of around 28 or 29 degrees or so. And so that axial tilt means that as we orbit the sun, we sometimes are orbiting the sun where the sun is more directly impacting the northern hemisphere. And then as we get to the opposite side of our orbit, the sun is more directly impacting the southern hemisphere and least amount on the upper hemisphere. And that's why we see winter at that point. So we have seasons at all only because of that. And otherwise, we would not have any seasons, which I think is kind of cool in and of itself. So I just have to, I'm going to bring up a calibration object here just to make sure that I'm still calibrating, because it doesn't, I just want to make sure that I'm doing right. So I'm moving now. One of the problems is as the colder weather sets in, and it's not winter by any means here, but it is cooler, the telescope contracts. It's in the cold all day long. It's not heated in here. And the telescope contracts, and fittings and so forth contract. And this causes problems because that means that bolts that were previously tight, holding a telescope, are now loose. And you have to go and cinch them up. Now, it means that in the summer, they'll be a lot tighter. And in fact, even maybe impossible to remove. So you have to be careful. But I have a sort of a happy mixture, and you know, we'll see what we get. So again, this was a photo that was 15 seconds, and just a second. Where's that beastie? How come he's not there? I see it's a little out of focus too. Oh, it's right there at the top. Okay. Well, this is helpful because I'm going to actually go into 4K mode, and I'm going to bring this up. And let me bring this down. I actually have to find a bright star, actually, because I see my focus is out a little. Let me make sure we can actually get to that star when I'm... Okay, so I come off. Do I see it? I don't see it there yet. Oh wait. Oh, duh. Okay, hold on. Okay, I'm not getting a star there to focus on, so I have to go find one, and I will go nearby. I'll be back. Here we go.
Okay, well, while you're looking, we have an interesting question from chat from Maddie.
All right.
If you could go back in time, which scientist or physicist would you most want to meet? And I'm going to throw in why.
Okay. Well, I guess the obvious answer for a lot of people is Einstein. But actually, that's not who I'd like to meet. I would like to meet Niels Bohr. Okay, Niels Bohr is the guy who founded the structure of the modern view of the atom. And without Niels Bohr, we wouldn't have had any of the physics breakthroughs that we've had. So Niels Bohr is a genius, but the guy was also, you know, as geniuses go, just a little bit wacky. But he's the guy that I would actually go back to meet. And the reason is obvious because I want to talk to the man who basically discovered the modern foundational view of the atom. Very, very cool, you know. I like Niels Bohr.
That's a very good answer.
No, I just think that's a very important element of our physics. We wouldn't understand any of the things we do about nebulae and other stellar phenomena if it wasn't for Niels Bohr. You know?
That's a good answer. Mm-hmm.
Well, I know it's a good answer because it's a really good answer because it's the right thing. It's the right answer, actually. So, you know...
Well, it's your answer, so it can't really be wrong, can it?
Sure, I could be totally wrong about it, but I hope I'm not.
No. Well, that's your pick.
Yeah, it is.
There you go.
Exactly. Alright, let me zoom in on this star here. Wait a minute. Oh, I might be fine. I think I may have something else going on here. Oh, I do. Is that right? Okay, that's right. Okay, so now I move up a little bit. And I will... Okay. So now, if I go back to where I was going before, this measured 92. I should see measure 92. And I will... And there it is. Okay. I was just working out my alignments again, doing a dynamic realignment of the scope. So, just wanted to do that. And as you can see, it's off a little bit because there's always a little bit of slop in the system. Not me. There's slop in my system too, I'm sure. But when it comes to this, you have to be wary of the fact that the cold will make things loosen up. So this telescope is in need of another full-scale calibration and alignment again. You know, you do it once every 6 months. So, but when the winter's coming around, you may have to do it sooner, and I do think we're going to have to do that sooner. Okay, let's go down to, let's say 6400, do a 15-second photo of Messier 92, a globular cluster that's up in the sky in Hercules, and it's 27,000 light years away as opposed to M13, which was less. And neighbor in the sky is M13, but M13 is a lot closer by thousands of light years. So there you see it. It actually kind of looks like a really interesting black and white photo, doesn't it? Like the old style black and white photos you've seen.
I see processing on the screen.
I know you do. And
But I take your word for it.
well, that's okay. See, chat knows that they're hearing me as I'm saying it. They're not having to wait 30 seconds. So they wonder what you're talking about all the time.
I love it. It's beautiful. No, they don't.
So now as I move around, you'll notice there's like this modeling in the black areas of the screen. Okay. This modeling is actually an artifact from the high sensitivity that we're using, which again at this photograph, at this photo at 6400. I mean, I could take this at a higher rate. Let's go to 20,000. Excuse me. And we'll do 15 seconds at 20,000. Sorry. I wanted to try and get just some southern nebulae, but I don't know if we're gonna be able to do it with the clouds down there. And I can't go very long tonight because excuse me. Tomorrow at 9 a.m. I have to start filming the season 4 continuation of oh, that's pretty. Season 4 continuation of What on Earth, and that starts tomorrow at 9. So that's going to take me all the way till the following day, and they shoot continuously. So I'll start at 9 a.m. and probably not finish until 1 or 2 in the morning, the following morning. And I have 18 stories to do, so that's a lot. And I asked them, how come you guys never seem to, I asked them this, I said, how come you never seem to have your act together? Why is it that you always have, why is it you always have, you always have to, go until like 2 in the morning? And the lady looked at me and said, well, you're the one that gets the most stories. You realize that, right? I go, I do? No, I didn't know that. And I found out that the reason is that they like having me, smash these these myths, and they like, I guess, my approach on talking about it. I'm not really sure, but I'm okay with that. I like that very much. That they're happy with me. I'm looking.
I like that too. Well, that must make you feel good.
It makes me feel good, but I do know that I'm in for a really long day tomorrow, a long day's work. Oh, let's see.
But are you going to get all 18 stories? No?
Will I get all 15 done?
18. I thought you said 18.
No.
Are you going to get them all done in the one day, or are they going to be back the day after, like for the week, or
the next day?
They
have
just
to be
come sporadically.
Yeah. Tomorrow is actually. The first story I'm going to do is actually one that I actually started, answering for them the last time they were here, but I didn't finish it. Now I got to finish it this time. So it will take a little extra time, but we'll get to all 15. Yeah.
Okay. Daryl has a question for you.
Sure.
He says that M13 look quite blue, and M92 looks quite white.
Yep.
Was that the sky glow filter causing the blue? Yes?
Absolutely. Absolutely correct. Remember, I took the sky glow filter off, so now you see a different look. And that's why I commented, oh, look, it looks like it's black and white. Because when the sky glow filter imparts an extra blue cast. Now, just for fun, let's go back to just quick view. Let's see if we can see this. Hopefully it's not in the clouds. Where are you? Well, we'll just go and see if we can see it. Moving. How are we doing here? Is that... Oh, might be in the clouds. Let's see. Let's see. No, it's there. There it is. Okay. Now, this object here is one we've seen before. It's actually a planetary nebula. And it's also your favorite, I think. That is you, Amanda, I think. This is the...
Well, I'm wondering, see, planetary nebula is what was throwing me. I don't know. Well, I know it's a nebula, but...
This is the cat's paw.
Is it the cat's eye nebula?
Cat's eye, I'm sorry. Yeah, cat's eye. Cat's eye.
Yeah. Yes, okay. That's what I was... Well, that's what I was going to say. I knew it was a nebula, but I didn't know it's a planetary nebula. Why is it a planetary nebula?
Because it's a star that has reached the end of its life cycle. And as it expanded to red giant phase, it left this sloughed off outer atmosphere of the star behind. Because the radiative pressure of the star pushing outward was enough to push the stuff outward. But as the mass of the star is lessened by this stuff sloughing off, the gravity of the star is lessened. And so that gas moving outward isn't necessarily going to come back. And so we see these sloughed off layers out there. And we're looking at this dynamically live, so not even in a photo. This is actually live. So if I tap the scope, you'll see it shake. You know, boom, 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 you know, so... So this is, you know, that's zoomed in. You can actually see that central white dwarf star. And it's hot enough so that it's causing the gases in the nebula. Now, those of you in the chat know by now, if you've listened to me before, you know that the nebulae, the planetary nebulae, the gases in the planetary nebulae are illuminated and ionized by that hot white dwarf with its ultraviolet radiation. And that ionization, when the electrons come back and they are reacquired, they drop an energy level in the atom, and when they drop, they give off light. When they increase, they absorb energy. So when you see a planetary nebula, you know that the light you see is what's called emission as opposed to reflection. All right? And as opposed to absorption. You're seeing emission nebulae, and that's what we're seeing here. We're seeing a planetary nebula that's actually, and Daryl's probably thinking, put on the oxygen 3 filter, put on the oxygen 3 filter. And because he's Daryl, I think I'll do that, just to give you an idea. All right?
Yay!
So you can see that the light coming from this object is actually light that's in the spectrum of, and in the realm of the spectral range of the oxygen 3, and that's something that I want to show you. So I have to take out the camera for 1 second, and now that we're aligned with it, okay, this is actually the size of it in the sky. That you see that little tiny dot, that's the size. So I know that we're focused at this point, and I can come back to a relatively near focus. Sorry about the red. That's the dome. And now I've got Daryl's oxygen 3 filter on the camera now. And okay, it's in. And now,
Which is so generous of him to send you to try out.
You know, I can't say enough about Daryl. He's actually wonderful. And he's excited about astronomy as I am, and he's just incredible. You'll notice now that the only objects that we see, and it's only vaguely visible, let me see here, is that star, and that it looks that strange color. Let's do 15 seconds at 20,000 just to see what we get. I don't know what we'll get. I won't even know if it's in focus. But let's find out. Now, oxygen 3 filters are primarily tuned for planetary nebulae, so we should...
Perfect.
Well, planetary nebulae, that, well, it's pretty obvious that it's working on this one. I just have to look at the focus situation here. Yeah, it's just gonna be a little more focused.
How many different kinds of nebulae are there? There's planetary nebulae, and there's
emission nebulae, and we have dark nebulae, reflection nebulae. So we have emission and reflection primarily. The blue is the reflection, the emission is the red hydrogen 2, H2, that we're familiar with. Now hold on a sec while let me try and...
That's okay. Give me a second to get some paper.
I'm trying to get to... I'm trying to just get us to a... Let's see. I'm going to try and focus this a little more. I may not... It's hard to see it. I can't zoom when I'm in this mode, but...
Okay, so planetary nebula are blue?
By and large,
And emissions are
planetary
red?
can be blue. Reflection nebula are blue. Okay, planetary nebulae are the cyan, that teal type color, like the Ring Nebula, and then they do have ionization of hydrogen as well going on. So you do get this H2 going on within these nebulae as well. Now I'm going to go down to 8 seconds and drop us to a much lower. I'm going to go to an ISO of 10,000 for 8 seconds to see if this shows it better and give me an idea if I focused it correctly. Again, the Cat's Eye Nebula. Let's see what we get. Okay. Now the blue cast, of course, is what?
No, I was writing things down, and I just looked up and glanced at chat, and I don't know, something just struck me as really funny.
Oh, okay.
They were talking about fig Newton bars, and some people love them and some people hate them, and blah blah blah. And someone said, what the hell is a fig Newton bar? And I don't know why, it just struck me as really funny. And yeah, I think I'm
funny.
cold. I'm not feeling well, guys. It's one of those things. It just struck me as funny, and the one time I wasn't on mute. I'm sorry.
No, I don't care. That's fine.
It's cute.
I went to a star nearby, which with the oxygen 3 filter, and kind of looks like the nebula. But I'm here only because I want to focus, and I need to zoom on a star that's relatively good size. So let's do that. As you can see, I need to focus a little bit better. Alright, so now we zoom in. Now I can take my focus here. Around fine, so let's do it. Alright. Now let's go back to the Cat's Eye Nebula. Moving back to that. Should be relatively quick and painless. Quick and painless. There we go. Alright, and now let me set my settings. 8 seconds at 10,000. Let's see what that gets us. By the way, I've downloaded a whole nother batch of music that I'm going to integrate into the SkyTour LiveStreams here soon. Hopefully it'll be stuff you haven't heard. Alright, this is a little bit, still too much. So I'm gonna come back to 4 seconds at 10,000. Ideally you drop the sensitivity as low as you can, because you want to have low sensitivity as best you can. So let's see. I want to be able to see if we can get that central star again with the OIII filter in place. And not quite yet. Alright, we'll see. Let's drop it. Let's drop the sensitivity now to all the way down to 1600 and go up to 6 seconds. So lesser sensitivity, longer exposure time. You don't compromise detail by having the high sensitivities. Let's see what we got. What do we got there? Oh, you can actually see the, if you look carefully, you can actually see, oh darn it, the focus is still out just a little bit. You can actually see how the outside of the nebula does have that kind of strange little wave on each end. Very, very cool. And that's something that you don't actually see a lot of. I'm going to go to 2.5 seconds at the sensitivity of 1600. And you notice that the processing time is shorter for the shorter exposures, of course. All right, now let's take a look at this. Wow. Oh, it's fascinating. It's just it is just a little bit out of focus still. And that bothers me because I really I really wanted it to be in focus. So I'm going to do this one more time. See, this is real astronomy, folks. You know, I'm going to go to a star again to do this focus alignment. And of course, when you're using filters, you're kind of stuck going to the brightest stars if the filters are fairly dense. And the OIII filter is kind of dense, as Daryl will attest. Alright, so let me let's get over here. Alright, out. In. Let's try that. Okay. That was it. That's the star, I think. Is that? Let's go there. Let's get this. Let's see if that's gonna work for us. 3.5 seconds at 1600. Now we'll see. All right. Oops. Let's zoom in. Well, that's better focus for sure. That lower star is actually looking good. So, the oxygen 3 filter may be preventing me from seeing that central star clearly, but I'm going to do 2.5 seconds. No, I'm not. I'm going to do. I'm going to go to 5 seconds at 640 sensitivity. Let's go see what we got. Wow, you can see much more intricate detail in that nebula. If you notice, when you look at the nebula now, although we don't see the central star anymore, we did when we were on regular white light, you can actually see the actual transparency at the left edge of the cloud. You also have some very interesting dark lanes in the middle, which you can clearly see. That's something that wouldn't show up with a sky glow filter, and it's something that wouldn't show up in white light. So this is really fascinating. This is a really good object for this. And while we're on the subject of planetaries, being that we are really close, not close, but it's literally almost over our head, I think that we should probably go look at the Dumbbell Nebula with this filter on. And I think Daryl is probably going to say, yeah, do that. So that's what we're going to do. Okay, moving.
Albireo actually wanted to know, and he's not talking about the propane torch the other day. He wants to know if you have actually ever used dew heaters for the telescope and the dome.
Well, since this dome is new from the summer, from the spring rather, I didn't install a dew heater yet. I have to. I gotta do that. And I want to, because we really need one. Okay, this is 8 seconds at 16,000 ISO sensitivity. Almost looking straight up at the Dumbbell Nebula. I'm just actually, this is an acquisition shot. I gotta make sure it's in there first of all. It's probably gonna be to one side. Alright, how come I don't see it at all? That's not good. Alright, well, I'm going to guess that it's... Let me do this. Let me do this. And then this. Give us that. Move over. I'll get this too high. Movements. Oh, wait. Okay, I don't know why I can... I'm expecting to see it here and I'm not seeing it. I don't know why. It's a simple thing. We go through it all the time. But you know what? I know how to find it if I can't see it directly. I know what we can do. We're going to go to...
Is your alignment? Is that what happened?
No, as I said, the alignment suffers from a variety of problems. Now, I see there's the ring nebula, and then it comes right in. And the dumbbell's not far away, so why? Well, you know, the dumbbell is fainter. Maybe it was in there and I just wasn't giving enough exposure time. Okay, while we're here, why don't we actually take a photo of the ring, and we're going to go down to, let's say, 6400 for 8 seconds and see how well this works. Oh, you know what I didn't check? I have dew on the inside of my dome. Darn it all.
Uh-oh.
That's probably what it is. No wonder. Okay, there it is. Now, that's a relatively low exposure of this. Let's just see what we get. Yeah, see? Notice you don't see any of the reddish stuff on the outside. That stuff is sort of excluded. You only see the oxygen 3. So here's what you do in astronomy. You actually you take specialty filters and you take photos in different light, it's called. So oxygen 3 light is this. Hydrogen, you know, singly ionized hydrogen is the H2. I'll explain why it's H2 when it's singly ionized, not doubly ionized. When you think two, doubly, you know, think of it that way. And doubly ionized, I'm sorry, singly ionized hydrogen is the red light, okay, the H2 regions. So when we take photos with filters that see only the different lights, what we do in a program like Photoshop is we combine them and bring them all together and make all new layers and bring all these different color layers with all these different specialty filtered imagery into one photo and combine them, all right? And so we stack them all together basically. These create these objects that we see and give us a nice nice ability to actually see the different interactions going on in the nebula based on a direct view of these particular frequencies, these particular wavelengths that we're looking at. And that's actually really cool, and that's something that is important to do, because that's actually how we do research. You know, when I did my research, we did the same thing. It was very important to do it this way, because if you didn't, well, then that was a problem. You know, you weren't sure what you were looking at. So I'm just gonna move the telescope down and check it.
So what kind of filter would you need to leave the red outer ring and take out all the bluey green in the middle and leave the black center?
What kind of filter would you need to want? I missed that. I'm sorry.
To put the red back, to put the red back and take out the blue.
Well, then you could just use a filter that's sensitive to H2, you know, the hydrogen. And then, you know, you could do that. There's filters for neutral hydrogen, there's filters for H2, there's filters for oxygen 3, which we see here, obviously. And so there are plenty of opportunities to do this. And I would think that one of the things that we would like to see that we would do is try and take the filters for the appropriate you know, emissions we know are in these nebulae, take specialty photos of those. So then, for instance, you could look at, say, just the oxygen contribution to this nebula by looking at an image like this. This is the oxygen contribution to M57, measure 57, from doubly ionized oxygen, which is O3. You know, oxygen III, you know, Roman numeral 3. We use the Roman numerals to delineate the ionization states. So, what do I mean by that? When we, when we see things like H2 regions, H Roman numeral 2 regions, that means singly ionized hydrogen. Why isn't it doubly ionized hydrogen? So 2 should be a 2, right? Well, the real answer is this. Atoms in their ground state, that is, where they're at the neutral energy levels, neutral state, those atoms, all right, that don't have a net charge, okay, remember ions are positively charged, you know, and the atoms in that ground state where there's neutral charge, those are called the singular state, the single state. So it's like H1 in Roman numeral 1 is the ground state hydrogen, okay? H2 is the ionized hydrogen, okay? O2 is the ionized oxygen. O3 is the doubly ionized oxygen. So it's a little confusing because you have to remember the ground state always takes up that one place, you know, the 1. So that's how that works. It's a little crazy, I admit, but, you know, we're astronomers. We make life difficult for everybody. That's sort of how it goes. Kiddingly, I say that. So, anyway, I'm going to do something that I shouldn't do. I'm actually going to go to the western veil now that the moon has set. And the western veil is almost overhead, and I see Milky Way overhead, but it's really not as good as it was that other night. But I'm going to try it anyway. So let me just move up there now. And I'll tell you why. Because the Veil Nebula is actually very visible in the doubly ionized oxygen realm. And since I got that filter in, we can try it. Now, it may not work because we don't have the best sky. You need a nice dark sky for this, and I don't think we may not see it. But that's 52 Cygni. All right, so here's what I'm gonna do. I'm just gonna take a picture I'll say 8 seconds at 320,000. It's kind of a crazy exposure to try. But let's just see what we see in the oxygen 3. Now the filter has a certain density and darkness basically. And when you see a filter with that kind of density and darkness, you have to compensate in the exposure. So imagine taking a photo, oh there it is, just to the right. There it is, that's beautiful. So let's go see that. Let's go over there. Oh, what did I do? I had it going too fast. So we're going back. So, as I was saying, before I rudely interrupted myself, a filter of a certain darkness has to literally be compensated for. And you have to compensate for it by increasing the number of f-stops, that is the longer exposure, more sensitivity. I'm trying to reacquire this now, just so you know. This is the Western Veil. So let's try and reacquire it. And so the filter is fairly dark, okay? And really we need to be able to acquire an image that's actually going to give us a lot of photographic data. To do that, we need to increase the exposure time or increase the sensitivity. Okay, there's 52 Cygni right there. So now, if I actually come down, you can just see it there. Let's go to here. Let's bring it here. This is sort of a nice spot. And I'll just do this to acquire it. We're going to see now this supernova remnant in the oxygen 3 light. That is the light that the oxygen in the nebula, the supernova remnant, is emitting at, because this filter passes through that light. And there you see it. Now, that's beautiful. And you see that it actually is fairly bright. The Veil supernova remnant is well known for being very bright in the oxygen 3. So now what I'm going to do is go back and try to tone down the sensitivity. Let's go to 20,000 for 20 seconds. Make it simple. And see what we get. Remember, the density of the oxygen 3 filter is fairly thick. You look through it, and it's not like looking through a very dark filter where you only see a reflection in it because you can't see through it. You can see through it, but it's very, very dark. That is to say, you're only seeing light through it that actually passes through the filter. And the only light that passes through the filter is the light that's in the oxygen 3 realm. And that's sort of a lie. I kind of just lied. I mean, if you hold it up in regular light and look out at trees, you can see them through there. You know, it's not going to be invisible. All right? So you will see it. But you won't see it very brightly. So in other words, it's a narrow band pass filter. So it looks right at oxygen 3, but it does allow other frequencies to come through. And that's the fact. So now, that last one, by the way, we just saw, you can see the remnant right there. And it's a little bit dim. So I'm going to do 25 seconds at 25,600 ISO. So I'm going up 2 stops. I'm going up 1 stop in exposure from 20 to 25 seconds. And I'm going up 1 stop in sensitivity from 20,000 to 25,600. Remember, I told you it's a 1-to-1 relationship. So whichever way you go, it doesn't matter how many you go up in, and whether you just increase the sensitivity or the exposure time, you're going up a stop every time you click one or the other upwards. And if you go up 2 of them, like I did, separately, I went up an exposure on one side and the sensitivity on the other. That's the same as going from 20 seconds to 25 to 30 and not touching anything else. You get the same result. The difference is at 20,000 ISO, yeah, see? Look at that. Wow, man, that's something, huh? Yeah, Daryl, I gotta take it back. You know, I was thinking that the O3 filter wasn't showing us too much, but check this out. I mean, look at this. You can see knots and convolutions that just are so incredible. Look at that. I mean, look at that. I mean, it's just, you follow it down to the star 52 Cygni here. And the other thing too, by the way, and you can't really see it there, but there's another separate part that's glowing in there as well. Isn't that beautiful? Wow, that's just beautiful.
It's really, I don't know, it's really cool to see that stream.
Yeah, and it's actually not moving radially. It's not moving up and down in the screen. It's actually moving, you know, from I think either right to left or left to right. Actually, let me see. I can tell you in a sec. It's actually moving. Yeah, it's moving from left to right on that screen. So it's on this view. So it's actually pretty incredible. Now I'm going to go down just a little more.
Okay, we actually have a question related to
I'm going to do
camera and telescope and stuff.
I'm going to do 25 seconds at 25,600 ISO again. And we're going to be looking down a little bit. Yeah, go ahead. Go ahead, Amanda.
Rio, he said he asks, would you get reasonable results with IR chip modification? The max ISO on his Pentax is 3,200. So he's thinking about updating his camera to an i7R11.
Yep.
But kind of leery to modify a camera like that. So what advice can you give him?
Is that the $3,200 camera?
Yes, it is.
Okay. I want to apologize to you. First of all, not you, but to him, because...
To Mario, okay.
Yeah, Mario, he's been asking me questions in Facebook, and Mario, thank you so much. I mean, it's wonderful. I'm glad you're asking questions, but I apologize. Today I was actually preparing all day for the film shoot tomorrow, so I didn't get to answer your specific question, which was a good one. So I apologize for that. I would say that if you can get a used camera body that you're not worried about, okay, then do so. I mean, the Pentax, beautiful camera body, not worth trouble if it doesn't go right. And you're not going to modify it yourself. You're going to send it out and you're going to have someone modify it for you, because otherwise you're looking for trouble. You know, and I'm sure I could look for trouble too that way. So I wouldn't do that, Mario. I would actually just sorry. I would actually just I would look for a camera body, a used camera body, maybe a Nikon, something cheap that you could modify and get rid of that infrared blocking filter. It's called IR blocking filter. That filter also has built into it, there's a second, it's like a sandwich. You have an IR filter and then you have a ultraviolet UV filter sandwiched into it as well. Because by having a UV filter, and we know this in astronomy, having a UV filter over, or having the ability to filter out UV, allows you to get very, very fine star images, and that's something that is kind of hard to achieve if you don't have the right equipment. So you want a camera body that can do the kinds of things that we're talking about. Now, the camera I have wasn't $3,200, but it was $2,500, and I do know that this camera can't really be modified to IR, and that's beautiful. Wow! And the reason it can't is because of the fact that there's a little LED inside this particular camera. And this LED is actually used to monitor the shutter, all right, which is electronic, but it's still monitoring the shutter. That said, that little infrared LED would then be seen by every exposure over a second, and that makes it impractical, unfortunately. I must have bumped the scope. It's a little bit bumpy there. But look at those. That is just beautiful.
Yeah, it's buffering a little bit on this side too.
It is?
A little, yeah.
Okay. That's something. I'm not done with this filter, I'll tell you that. I gotta try out a few more things here. This is cool. Let's see what I got in my southern hemisphere. I want to see your southern skies. Oh, what do I got? Oh, I got high clouds over there. This looks nasty. Oh. Yeah, they're encroaching. Darn it all. Urgh. I guess that's you know, that's nature's way of saying, you know, you gotta go to bed early because you're gonna be up early. You're gonna be up all day and almost all night tomorrow. You know.
You know what? I swear I was thinking of that before you called, before you started the stream. I was gonna say, is there a set time you want me to keep my eye out to say, yo, it's almost midnight or it's almost 1 or something like that? Give you some kind of cue, and I totally forgot about it until you started mentioning it. I'm like, oh yeah.
Yeah, that's okay.
So.
I do want to do one more thing though while I'm here, and I'm gonna just bring up the previous object we just looked at. I'm gonna compare this photo, which was 30 seconds, at come on, I'm stepping on my shoelaces. 25,600 ISO. Okay, for 30 seconds. All right, I'm gonna compare this one, and now I'm gonna remove this filter and put on the other, and I have to refocus, so I'll have to come back to this, but that's fine, I can do that. So now let's get this off of here. Alright, and there we go. And let's make sure that's covered. You don't ever leave filters and lenses out where they can actually be bothered by anything. And let's put this back on. Now I'm using the other, the Sky Glow again. All right. So let's do that. All right, let's see here. Is that right? Doesn't feel right. Oh, there we go. Okay, so this goes there. There we go. Okay.
And I'm guessing you're doing this by feel because it's so dark in there.
Of course. Of course, you know.
That's a professional, guys.
No, it's called flying by the seat of your pants. No, it does come from years of experience doing this in the dark. Hey, how about this? I actually changed film plates, which were for purposes of doing the our specialty program for studying the distances of nearby stars, called the parallax program. I actually had to take photographs using a refractor, a lens system where the 20-inch refractor was about 35 feet long, and as I mentioned before, the whole floor moved up and down to meet it. I would actually have to take that telescope and change the film emulsions completely in the dark, and get new plates put on, and that was really not easy. Okay, I'm gonna just focus on 52 Cygni. Yeah, this is how you want to focus. This has the Sky Glow filter on it now. Okay. All right, so let's now. Okay, let's focus. Here we go. Come on. Okay, now we focus. All right, I'm gonna do this by. I'll come back down manually. I'll bring it back in a second. Okay, we'll come back down. There we go. Now let's get this focused. Alright, now we focus again. Alright, now let's do another exposure. This one will be again 30 seconds at 25,600. We're comparing apples to apples now. That is, we're going to see the results of the SkyGlow filter, which we have in here now, to the oxygen 3, which we just had in there before. And the results are not going to be cut and dry. You're going to think they are, but I'm going to explain to you why they're not. And this is why Daryl spent the time and money to get this particular oxygen 3 filter, which he sent to me to borrow and use. Once again, Daryl, you're a man about town. Fantastic, and I appreciate it, because this is really interesting research that we can do here. And by showing the difference between the filters, people get an idea of what they're for, what they do. Now, the SkyGlow filter, as you'll see, is really more about taking a photo that's visually appealing. That is, it preserves the original colors of things. Oxygen 3 filters are a research tool. They will be taking pictures sensitive to that particular emission. All right? Now, here we go. If you take a look at this image shows you 52 Cygni at the top, and you see the blue nebula that was actually more detailed, but you also see the other emission of the H2 next to it to the left. You can see the colors. All right, now let's go see the other image. Okay, this is the image, and let me make sure this is the apples to apples. This image here. Sorry, I'll do it this way. Yeah, this is 30 seconds at 25,600 as well. And this is with the OIII filter, okay? You might say, well, wait, the other one looks better. But what you're missing, what did I do? Oh, sorry, I went the wrong way. Let me get out of this. Sorry, just went the wrong way. What you're missing is that this OIII filter image shows us specific convolutions and details. In spite of the high ISO number, the high ISO sensitivity, you can see specific convolutions and details in this image, like there. Now if we go to the other image, okay, let's go to that we just did. Okay, this is that one. Now let's go into that. Okay, if you notice, the details really aren't as significantly, they don't stand out as significant. Okay, here's a star. Let me go back to that. Right there in the middle, there's a star that's actually illuminating that little strip of nebula right through the center. Okay, it's actually part of that. Now, if we go and look at the other oxygen 3 nebula, okay, oxygen 3 version of this, okay, and zoom in, look at the difference. Do you see how convoluted and detailed it is? You can actually see the twisting and turning gases inside that little area alone. Okay, you can see it. I mean, it actually has a distinct knottiness, okay, to it. And if we look at the other one, okay, that's the other one. If we look at this one and we go in there, although it's in color, where's the knottiness? It's not as obvious. In fact, we're not sure whether the noise from the chip is what we're looking at, but the knottiness isn't that clumpiness that you saw in that object. This looks very regular. It looks smooth, relatively. Compare that now to the oxygen 3 version, okay, which is this one, and we go in there and look at that. You can clearly see areas of light and dark. really detailed areas within that nebula. Now just imagine you take 25 images like this, okay? And you stack them together. Then you take 25 images, okay? Like this, with the sky glow filter, and stack them together. And then you take those 50 images together and you add those together. And now you will get a very detailed area around there in the star, around that little tiny star over there. You'll get very detailed areas around 52 Cygni, and you will end up being able to produce an image of the nebula which is so much more detailed that it will basically be jaw-dropping. So, on SkyTour LiveStream, our mission is not to bore you to tears by taking image after image after image after image of these same object over and over, but to show you a variety of images. What you don't know is that on the nights that I'm downtime, I'm out there doing the research anyway, and I'm doing those types of images, and I'll make those available to you. You'll get to see them. I did one such sequence of the Iris Nebula the other night. I did one such sequence of the Dumbbell. So those kinds of things are coming, and I'll make sure you see them. But so this is really pretty. For visual impact, I choose the Sky Glow. For research impact, I must choose the Oxygen 3 and any other that I have. I mean, we do have, there's some special filters. I actually have a filter wheel, electronic filter wheel, which goes, at the camera, and I can just cycle through the different filters, boom, 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 and take a bunch of exposures. That is something that is very valuable. And so you have, a neutral hydrogen filter, you have neutral density, you have other filters. And when you're done, you end up with just a tremendously varied array of exposures, and then you're free to manipulate them all you want. And speaking of that, I've been using Photoshop a lot more to do image processing. And people, those of you in chat who've heard of Photoshop, you think, oh man, that's a $400 or $500 package. Yes, it is. However, I didn't pay $400 or $500. I actually subscribe to Adobe's Creative Cloud. Creative Cloud gives you access to these applications for just a few dollars a month. Meaning, I pay $9.99 per month. $9.99 a month. And I get Photoshop. Okay? My son's in film school, so for an additional few more dollars a month, I give him Adobe After Effects so he can do editing. The latest version, and it's always updated. So I have the latest version of Photoshop on my machine at all times, and it costs me a subscription rate of $10 a month. So for those of you who don't want to, part with that kind of money to buy a package, just think about using it. And if you need it for if you want to try it for 3 months, that's $30. To try Photoshop. And if you can learn Photoshop in 3 months and see some value to it and do astronomy and get some really cool imagery, then you can. Then you might want to continue to subscribe. But, as I said, Adobe Creative Cloud is the way to go. You get some access to all kinds of applications with Creative Cloud. You get access to Lightroom and other applications. You've got there's managers that help actually manage the imagery you're taking, and not to mention 10 to 20 to 30 hours of tutorials that you can watch over and over again and learn something new every time. Trust me, I did, and I still do. All right, so I'm not, I don't have all the answers, but I do know that when I use Photoshop through Creative Cloud, I have the latest version, and I don't have to want for anything. I have everything an astronomer could ever want when you're talking about processing your photos. And if you're not an astronomer, you don't need it just for astronomy. It's great for everything else too. So, people think, well, it's such a deep program. Well, yeah, it sure is. But you only have to use one or two things in the program to get exceptional results far beyond anything you ever thought you could do. So it's not like you have to know everything about the program. It almost sounds like I'm looking for a sponsorship from Adobe, but that's not where I'm going. I'm just telling you the truth here. I'm excited about it because I use it. Like this image, okay? See this? I'll give you an example. Okay, you look at this image. You see how you get that modeling in the dark areas? That modeling in the dark areas is something that is the reason that astronomers don't like to use high ISO or high sensitivity settings. They'd rather take a much longer exposure at a low ISO. I understand that. They won't get as much noise. I could take the same image that I've taken here. Again, remember the one-to-one relationship. Okay, this was 25,600 at 30 seconds. If I went up to 60 seconds on the photo, which I can do, then I would find myself, being able to drop the ISO down to basically being in half. So from 25,600, I could go down to 12,500 or 12,800 or so, and then it would be that much less. But I don't have a 60-second setting that's just automatic on here. I'd have to get a remote and do it that way, which is not a big deal at all. I can actually do it through the iPhone or the iPad. And I'm running music on my iPhone that you're hearing, and the iPad runs the telescope. So I just choose to stick within the 30-second limit that I have within the camera. But this modeling is something that you could get rid of if I could go to longer times. But then I'd have you. I'd have you folks sitting there waiting on a black screen for a minute at a time. And what if I want to do 5 shots? That's 5 minutes. Oh man, you know what? I understand this. I understand impatience, and I wouldn't actually put you through that. I just wouldn't do it. So I think that there's plenty we can see when we just look at things like this. Okay, even with the noise, it's just beautiful, and I don't think I haven't seen any negative complaints about this. But if you have issues, if you'd like to see something different or try something different, you just let me know. I am not going to sit here and say I have all the answers from this stuff. I will be happy to try it. Again, I'm taking 52 Cygni down the bottom. I'm going to do a 30 seconds again at 30 seconds at 25,600 of the northern part of the eastern veil. So, sorry, western veil. Yeah, I forget which way I'm pointing here. It's opposite from where you look in the sky, because west is where the sun sets. West is the side we're on right now of the veil. The veil is actually a large circular remnant. If you look at it in the sky, it has a rough circular look to it. And the star that set it all off is, of course, not visible to us. But when a supernova happens, stars of a certain mass, once they explode, they can leave behind a neutron star. The neutron star is the collapsed rest of the star that was there previously. And, oh wow, that's pretty. Almost looks like a spider web. But the neutron star is like the collapsed star. And neutron stars can be a few kilometers across. And then that's how collapsed they are. And they're also very, very dense. A teaspoonful of matter from a neutron star would, weigh as much as Manhattan Island. So it's really, really big deal here with these heavy masses.
It's crazy that you can even make that kind of a reference.
I know, right? And the oh, you mean just because the number is on the top of my head? It's just,
just what a weird thing to compare it to.
I try to put things in terms that people just understand every day, and you know, they know what it's.
No, I like how you explain things, but I mean
it's just kind of weird.
to even figure it out in the first place, and then to be able to, I don't know, just equate it like that.
Yes, it's true though. I have
Math really does stupefy me, so.
Apparently I have no life. I spend time figuring this stuff out.
That's cool. That's a really interesting thing.
Yeah, and the thing about now, if the star was a little bit more massive than a neutron star, or I'm sorry, than the progenitor that caused a neutron star, and the word progenitor means the star that caused it. So if the star was more massive than the progenitor that caused just a neutron star, then as that core collapses, it wouldn't stop at just a neutron star. It would continue to go down to what? You know? As it collapses.
Sorry, from a.
It would collapse as a large star would collapse. The core would collapse.
To a red giant.
No, it would actually be collapsing if it went past the neutron star stage. If it was a certain mass, then it couldn't stop going to a black hole. And that's that comes after the neutron star. All right. Now, what's interesting is in the cores of many galaxies. Yeah, as you can see, my battery is dying, so I have one more battery I can put in. I believe I do, yes. And hopefully that one's at 100%. But I am going to be knocking off soon anyway. But in the cores of these active galaxies, you actually have large black holes. That's actually been a ongoing study for many years, actually decades. And we see these objects in the cores of the galaxies, and they tend to put out an awful lot. Yay, 100%. They tend to put off out an awful lot of energy, and there, as active galaxies, you may have heard the term quasar, and that means quasi-stellar radio object, and that's the cores of these active galaxies were giving off these intense radio frequencies. And then, as it turned out, some of these galaxies are actually spewing high-energy gamma rays out as well. And that's because a black hole is obviously, think of a black hole as a spherical object, a collapsed star, singularity, and it has like an event horizon, meaning there is an outer boundary, so to speak, beyond which entry would prevent any of the light from that object ever to escape again, from ever escaping again. And it's an accretion disk. It's like a plane of the solar system around the sun. If the sun was a black hole, then an accretion disk would be all the dust and dirt and molecules and gas and additional stars, perhaps, that are orbiting it, and they would eventually be pulled into it based on the fact that black holes tend to eat things. Now, if the sun was a black hole, just so I can say this clearly, the Earth and all the planets would just continue orbiting it because the sun, wouldn't be changing its mass. However, if the sun increased its mass, then all bets are off. Okay, then things get pulled more because the orbital speed isn't enough anymore to prevent them from spiraling into the sun. So, as a black hole eats things, it grows in gravitational strength, and thus eats more stuff and more stuff. So that's how that works. Now, if we look at the these active galaxy cores in the centers of these galaxies, these sometimes can spew these gamma rays I was telling you about, and they go like above and below the accretion disk, that disk of matter swirling in, and sometimes those are pointing right at us from these galaxies, and we see these gamma ray bursts coming from galaxies. Not all gamma ray bursts come from these galaxies, but some do. And the ones that do, they actually have a term for them, which was invented actually in the 70s, and it's called blazar. And that's, goes with quasar, and blazars are actually quasars that have that gamma ray, basically lighthouse beam aiming at us. So they're the same thing, and You know, they're just their activity is such that we actually get that emitted gamma ray energy here on the Earth, and we see it from the galaxy. So that's that's the whole thing with these black holes. You know, we think there's mega-sized black holes within these galaxies. You know.
And actually, David is just taking a break from teaching. It was on. So he's been watching, but it's been on mute, and he missed, I guess, the ID of this long streak down the middle of the view. What is that?
That's the Western Veil Nebula. It's actually the one of the elements of the supernova remnant that's in Cygnus. So an element of the Western Veil. All right. It's and the Veil Nebula is the entire round, artifact in the sky, but the Western Veil is that part we're looking at. Now we're going to the Eastern Veil. We're going to look at the Eastern Veil for a bit. Again, we're using the Sky Glow filter here. We're not using the Daryl's filter, the Oxygen 3 filter.
And speaking of Daryl, he had a very interesting comment, and I want your opinion on this.
Sure.
He said that there's news out in the last few days of another gravitational wave event. They think it was two neutron stars colliding, and there was an optical diffraction as well, a first, evidently. Do you know anything about that?
I know about the first one. I didn't know about the second one. I haven't. I was focusing on my What on Earth filming, so I didn't actually view that yet. Wow. So I will get to it though. I'll look that up. I'll be back onto that in no time. That sounds pretty cool.
Well, can you explain?
Oh well, yeah.
What he even means by that comment?
Yeah, actually, the thing that Daryl's talking about is first of all, Einstein predicted that gravitational waves would exist, but he didn't ever expect that we would be able to see them or find them. Of course, he didn't know that we would be seeing black holes in the way that we are. So, that said, when we saw, I think it was a couple of years ago now, two merging black holes, they actually ended up giving off a gravitational wave that was detected by two instruments, one in Washington State at Hanford and one down in Louisiana. And these instruments were able to see these gravitational waves coming off these black holes in collision. And if Daryl's talking about another event has happened, then that's really good for us. That's awesome, because it really proves that Einstein was right, that gravity is in the form of waves, just ones that we, like light waves, we know how to reflect light, we know how to do all kinds of things. Oh, there we go. We know how to do all kinds of things with light. Bend it, refract it, stop it, generate it. We don't know how, on the other hand, to do the same to gravity. We just know how to calculate its value. We don't know anything else about gravity. We just know that it's the force of gravity is, the universal constant G, capital G, times the mass of object 1 times the mass of object 2 over the radius between them squared. And that's all we know about gravity. We don't know that gravity, how it works. We don't know how to stop it. We don't know how to bend it. We don't know how to reflect it, refract it, generate it, stop, halt it. If we knew how to do that, then you see anti-gravity is something we would have access to. And I don't think that it's that far off, believe it or not, because if we can see gravity waves, is it possible that gravity particles, gravitons, are not far behind? Now, gravitons are the analogy to photons in the light world. And if we see that we have gravitons as well as photons, and if we see that we have gravity waves as well as light waves, then it stands to reason that since the universe provides templates for the mechanics and physics for all these things to exist and operate, and the laws within which they operate, maybe it's possible that we will have the ability to, say, reflect a graviton stream or refract gravity waves and change the direction that gravity's moving. I mean, these things are now becoming less science fiction and more science plausible. I'm not saying possible, I'm saying plausible. And again, there's a lot of science between here and there, a lot of discovery between here and there that has to happen. But just think, it may not be that long before we will be able to basically have anti-gravity. And then, oh my, and then
we get our hoverboards.
Then we'll have hoverboards, exactly so.
Yeah.
You know, and it's not like the hoverboards. You're thinking of hoverboard. I'm thinking, oh, we're going to colonize the solar system for pennies. You know, because the bottom line is, here we are, species that we are. We're kind of sort of primitive in our own way, but we've managed. I'm sorry, I'm just looking at this object here, and it's like this is the, you know, this is so beautiful. It's actually the Eastern Veil, and look at that. You can see the colors very, very beautifully, and I'm just astonished. I love these colors in Eastern Veil. Again, the blue, that's oxygen 3, and the reddish areas, those are H2, you know, ionized hydrogen regions. And it's just, and this is actually a photo that was taken at, I believe, we'll see here, it's 25 seconds at 80,000 ISO. So that's a that's a fairly fairly highly sensitive shot. And just for fun, you know what? I'm gonna do this. I'm actually gonna I'm gonna go in here and I'm gonna go up to 160,000. So I'm gonna double this and do a 25-second shot at 160,000. I mean, I don't know what to expect with this. I mean, that there's a certain point where you lose the benefit, and it might be just a bright blown out thing, or but we'll find out. I want to see if there's any other detail in there that I can actually coax out of this, because that's what I do. I coax data out of the shadows. That's my job. I love it.
Well, that's what I was thinking earlier. You said if you did like a minute-long exposure, people would get bored and they'd just be looking at a black screen. Well, no, because you tell us such interesting information and explain things that were and what you're trying to do and step by step how you're doing it. And then the pictures we get are that it's worth the wait every time anyway. So, I mean, I'm going to take the liberty of speaking for chat and say, maybe not like a 20-minute picture, but like a minute or two. It's not like it's going to be dead air or anything. I think people would stick around. People stayed for what? 3 hours to watch you burning that torch off. So.
Well, that was a specialty thing. Yeah, because they knew the fireworks were coming. No, they didn't. I'm just kidding. But no, this is true. And I think and by the way,
that's gorgeous.
Isn't it pretty? No, it's also.
I love those colors. Oh my gosh.
It's overexposed. So, just for fun, I'll bring it back. Don't worry. I'm gonna actually come back to.
That's so funny. I was just thinking that, Jello. Our friend Sarah Fezio, she's an artist, and this looks like something she would create with her paintings.
I
please check her out on YouTube.
Yeah. Does Sarah have a site that we can give for her?
Yes, Sarah Fezio. SarahFezio. I'll get the link for you in a second. And
do that.
I think a lot of people in here already subscribe to her, but
No,
in a lot of her pictures, I do get a really space kind of, whether she means to or not, I think space and...
well, that's kind of like,
Yeah,
that's why she's
Kelly
probably
is,
with us here, because this appeals to her. So Sarah, I hope this shot that's about to show will give you a lot of inspiration. It's a beautiful Gossamer Nebula. It's several light years across, all right? And this is the Veil Eastern segment. And when you look at this again, because I'm using the high sensitivity, notice all the color modeling you have in there. That's called color noise. The noise within the color as well. So and that's never good. We don't like that. So we want to try and figure a way around that. So again, in Photoshop, which you can subscribe to for $10 a month or so from Creative Cloud, you can remove that noise. You go to Filter, Noise, and then there's actually a Reduce Noise selection, and you can then get rid of much of that color banding or color modeling. And then you could play with something called the curves and bring out just the nebula detail and make that the space around them turn darker toward the black like you expect it to. I make it sound easier than it is. I mean, it does take, you know, it's an art. So it takes time to get to that point where you can do that. But it's worth every bit of going through the time to do it, because you know, if space photos are your thing, there's really no better tool. So do you have Sarah's? Did you give Sarah's link out?
I did, and Jello did, and Rockstar did.
Great. And Sarah's listening to us today. She's listening to us today.
No, she is in Texas, but she is safe.
Okay. Good.
As is Jello. He's been streaming the some of the scans, the live scans in Texas.
And did he scan?
And our thoughts are with all of you in Texas. Our friend Daryl was affected. I didn't realize that. People just told me in chat today, so hearts go out to him.
How was
Please
Daryl?
stay safe and dry.
He's in Colorado.
Pardon?
Daryl?
Derek.
Oh, Derek. Okay, yeah, sorry.
Yeah, friend Bruce Derek, yeah.
Yeah.
No, I don't think Sarah's listening tonight, but Jello is in. And,
all right.
Yeah.
Yeah. I don't know if it. I saw that. It's one thing on YouTube. It said, Houston, we have a problem, and it showed the highway, and the highway sign, the overhead highway sign, the big green sign you see over the highways, and it was like water underneath it. It's all water for as far as the eye could see. No highway visible. It's crazy.
Yeah, I saw a lot of pictures like that too.
That's very bad.
More Jello, please. The site as well, and a new house. So if we can get those links in there.
The what?
That's what I love this community.
Yeah.
Oh no, I'm gonna get the links in there for everyone, and yeah, it's a really nice, supportive community, and everyone's helpful and nice, and.
No, I gotta tell you,
I'm
taken aback by how wonderful everybody is, especially those that come to our SkyTour LiveStream. I'm just very impressed, and I'm very pleased and happy to be able to bring you things that you can enjoy, and I'm just, you make me proud to do it. So hey, what can I say? Rodney Dangerfield will say, hey, I get no respect. But you know what? I do get respect. And in turn, I return it. Oh, yeah. Our sky is getting diminished. But before I do that, I just want to do one more thing. I'm going to move now. Yeah. Come back. Come back, little guy. You'll make it back. Oh, come on. A little more. A little more. Oh, it's not going to make it. I'll have to pull it back now. Yeah, there it is. I just love this double star. Okay. I shouldn't even have to tell you what it is, because I will zoom in on it and you will see it. Okay, and when you see the two colors, you should recognize this double star. Does anybody in the chat recognize this double star?
I'm waiting for it to come.
Yeah, no worries.
Buffering.
Oh, I really wish you could hear it.
It's very pretty anyway.
It is. It is beautiful.
Now I would say because of their color, they're higher to mid in the spectrum scale.
Very good. That's a good, excellent.
I don't know if spectrum scale is the right term or not, but
it's not. But you're close in the stellar classification.
You know what I meant.
I do, and that's just that's why I chose not to, be picayune about it. Yeah.
See, I'm getting a hint, but
somebody hinting at it.
Yeah, someone's guessing.
Oh, what are the guesses?
Oh, Albireo?
Correct.
Yay! Okay, because Daryl said it started with an A,
Oh,
and because Jay had guessed Sirius before that, then he switched it to Andromeda, and then Andy said AN, but then Daryl said head of the swan, foot of the cross, and I actually got it from that.
Oh, you said Albireo, you didn't see it in the.
No, that was
Very
my
good.
guess.
Oh, very good. Well, you're absolutely right.
Yay!
Now, here's something I didn't tell you before, though. Now, these two components are 430 light years away, okay? And they're separated by 4,620 astronomical units. Now, that's not the record for tonight. We saw two stars that were separated by 14,500 AU, if you recall. But these stars are separated by 4,620 astronomical units, and they orbit each other. But it takes them 75,000 years to orbit each other. That's how big their orbit. That's how long their orbits are. Isn't that incredible?
That is incredible.
Yeah. Yep.
So okay, so I'm sure you've told us before. Is one of them? Is the smaller one on the left
Go ahead.
possibly an O? No.
Well, you would think so because of the blue. That's very good.
Well, but it's not bright enough blue, so it would have to be down a little. But the other one, it still has a tiny. Well, to me, and again, it could be my eyes. The bigger one on the right looks more white, but like it has a little hint of a blue.
Yeah, well, let me just.
So I don't think it would be that far down.
Let me do something to help you with that.
Are you going to defocus it?
I am.
I am learning.
You are. Now, don't forget, I am using that special filter to eliminate the sky glow. That is the lights from sodium vapor lamps. And that frequency is close to the stars on the right. So it's going to tend to make that star look a little washed out in color when the stars should be a little more yellow than this. A little more reddish, a little more, actually orangey. Okay? The blue stars, it won't affect this except make them look a little more blue. Okay? Than they should. Remember, we're looking at this with the filter. If we looked at it regular, the star on the right would be very clearly orange. The star on the left would be very clearly pale blue. So what are we looking at? For that orange star on the right, okay, in Albireo, remember the star on the left anyway is, you had mentioned, you said O, but maybe a little bit later. And what would that be?
B.
Yes, exactly. And it's actually a B8. Okay?
Okay.
So it's spectral.
I'm still not getting the number part, but that's okay because a lot of these things have number parts after them. And
yeah, B0 is an early B. B9 is a late B, meaning what? What's that mean? Well, in terms of its temperature, you can rate the stars on basically 10 different levels. Think of it that way. A B0 is the hottest of the B stars. A B9 is the coolest of the B stars. Okay? But a B9, okay, is still hotter than an A0 star. Okay? Because that's next. OBA. And then A0 is the hottest of the A stars. And A9 is the coolest of the A stars. See, it goes like that. Now, an A9 is not the temperature of a B9 at all. It's much cooler. Just as an M9 is much cooler than a O9 star. So the number designation just talks about basically the level to which they are, their energy is such that the 0 in the classification, the B0, would be the hottest, okay, of that particular stellar spectrum classification, okay? Spectral classification. And the 9, which is only goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the 9 would be the coolest of that particular stellar classification for that star. Follow?
Yes.
Okay. Now, Vega is an A0 star, all right? So, Vega, although it's something like 26 light years away, it's very bright in our sky, is cooler than this B8. All right? We know that right away because of the spectral classification. And the B8 is also a main sequence star, okay, a Roman numeral V, 5. So it's a B8-5, and Vega is a A05V, and the star here, the B85, is there on the left. That's a normal fusing regular star, dwarf they call them. So it's doing hydrogen into helium basically. But the star on the right is a K3 giant. All right, so it's actually not on the main sequence like Vega and the B8. Okay, it's actually off the main sequence. It has migrated away because it stopped doing its hydrogen burning. So this star actually has no main, there's no real hydrogen fusing going on in this star anymore. It's now fusing other stuff into other things, all right, which will eventually come back to us through the periodic table. So this is all part of the stellar physics and learning about what the stars do and how they operate. Okay. Again, the filter is really making these look pretty odd. I grant you. But this is pretty nice. You see when it's not so distended in this particular case using this filter, you can see the colors pretty clear here. Okay, you see the orange pretty well. And then, about there, seen pretty well.
So now the orange one, again, you said it looks washed out.
Yeah, because of the filter.
If it's actually orange, I would guess that one would be a G?
Well, G stars, okay, are like the sun, and they're more like in the white to yellow. The G0 might be a little bit whitish, and the G9 might be a little bit yellowish. Okay. After the G star comes the Ks, which is what this star is. It's a K3. So it might be a yellowy orange as a K0, but as it moves up, it's going to become much more orange as a K9. And again, that's temperature related. So this star, the K3 giant, is already past the main sequence part, and depending on its mass, we could have a very interesting future by staring at Albireo. Who knows what will happen to the B8 after the impact of all the stellar material when the K3 either goes supernova or drops down to a neutron star, if it does that. So there's an awful lot of variability we don't really understand. I would love to remember in the Magellanic Cloud, which is the large companion galaxies to our Milky Way, Remember, we have the large and we have the small Magellanic Cloud, and you can't see them from the north. They're down south, right? I would have shown them to you 1,000 times already. These, those in that large Magellanic Cloud, we had supernova 1987A, I think it was, and it was actually a supernova right nearby in that companion galaxy. And it looked really cool. I mean, it was amazing. And you could visually see the light echo, that is to say, the expanding ring sphere really, of light coming from the supernova explosion. You can actually see that moving through space. And it took time. You have to spend years watching it, but you saw the light echo moving through space. It was incredible, and you can look that up online. It's all out there. Yep. Neato.
That's crazy.
Yeah. Indeed. So,
we do have a few questions before you call it a night.
Sure, go ahead. This is the last object, so I'm not going to show us anymore because I do have to get up early tomorrow to film, so I'll do that.
Okay.
Sure, go for the questions. Go for Papa Palpatine.
Okay. Actually, they're both from Jay.
Okay.
One, he wants to know, could a satellite fly through a star?
Well, from our visual perspective, it could pass in front of a star, but stars are, of course, very, very far away. Satellites are only a couple hundred miles up at the minimum to a few thousand miles out at a maximum. So, there's no stars close enough for it to actually hit a star, not even our own. But a satellite could pass directly in front of a star. And as far as the timing, that would actually be kind of spectacular because the star could just wink out for a second. Because a star is really just a point source. Now, these guys look like they have some size to them, but they don't. Okay, we only see stars as points of light. And the reason is because they're so far away. Even the largest giant takes special techniques like Betelgeuse, okay, the upper left-hand star in the constellation of Orion. Okay, it's a bright red supergiant, and that star has been resolved as a disk in the sky. And I forget how far away it is, like 580 light years or something. Well, anyway, it was resolved to a disk in the sky using a special technique called interferometry. And by taking and resolving it to a disk, we could actually see and map the surface of Betelgeuse. And we sort of saw that these red supergiants like this didn't have a consistent surface. They were actually, they had kind of modeling all over them. They were sort of a strange conglomeration of surface detail, which is really weird. Now, we didn't see this very clear. It wasn't obvious. It wasn't saying, hey, look at that. Look at those star spots on Betelgeuse. We didn't see anything like that. It was just a rough map, and it was very, very hard to get that, okay? Yet, with normal-sized stars, remember, Betelgeuse is large, with normal-sized stars like Alpha Centauri, the closest star to us, it's only 4 light years away, 4.3 and some change light years away for A and B Alpha Centauri, because it's a triple star system. A and B are roughly like the sun, and then C is the red dwarf orbiting both of them from a much farther distance out, and that's a red dwarf, a red M star. And it turns out that particular M star, Proxima, okay, which is Alpha Centauri C, okay, A, B, capital A, capital B for the two main components, and capital C for Proxima. Proxima has a little b around it, that is to say, a planet. And, that is amazing because it's the closest planet closest exoplanet to us. Now, that said, A and B are the closest stars, and they're about sun size, and we can't see them as disks. And they're the closest star to us. But a star like Betelgeuse, hundreds of light years away, we could actually resolve as a disk because of the fact that we use a special technique. We can't use that same technique on Alpha Centauri A or B because the disk of the star, even at this closer distance of 4 light years, is simply apparently not big enough to resolve. To give you an idea, and this is one I thought of as well. If you when you look in the sky at the star Alpha Centauri, again, 4.32 light years away. It's the only that's just the nearest star to us. Well, actually, Proxima is actually the nearest star to us, but for this analysis, I used Alpha Centauri A. That star, at that distance, if you wanted to see that star as a disk, here's the difficulty. To see it as a disk, imagine a quarter, a 25-cent piece. How far away from a camera, and you're taking a picture of a quarter, how far away would you have to move that quarter so that the diameter of the quarter would be the same size as the diameter of Alpha Centauri A in the sky is to our telescopes? How far away from the camera would you have to move the 25-cent piece so that it was the same diameter as the star, in the view?
8 miles.
Good guess. And
1 mile?
Huh?
Mile?
Well, see, you tend to think that it's, a few miles or something. You'd have to move it 750 miles to see. And now, we don't even have any telescopes here on Earth that could see the face of a quarter 750 miles away. Okay? And that's the kind of resolution we need to be able to see the disk of Alpha Centauri. And now, just for the record, seeing planets that are 10 to 20 to 100 times smaller than the disk of the star is a feat that I can't tell you how amazing it is that we can actually do that. But studying the light curves, seeing the tiny bit of dimming from this tiny little fractional sized planet, dimming the overall light of the star on a regular basis as it goes around the star, is an incredible feat of engineering and technology. And the Kepler Space Telescope looked at 100,000 of those stars in Cygnus, in fact, kind of right near the veil, sort of near the veil. And it looked at these stars and found out, that about 4,000 of them had planets. And of those, a certain percentage were super Earths, and a certain percentage seemed to be in the habitable zones of the star. And I've said it before, but such that when we looked at the actual number of exoplanets that are like the Earth out there, we could see that it turned out that most of the 100 to 400 billion stars in our galaxy, we don't even know the real count of our numbers of stars. That's how little we know about our own galaxy. Of that count, 10% might have Earth-like planets just in our galaxy. Now, that means either, let me say, 10 billion planets out in our galaxy, or perhaps 40 billion in our galaxy. So it's actually a pretty incredible feat that we can have made these determinations and learn this stuff. So I'm pleased that we're moving forward in science, and for all we know, there's so much we don't. And like looking at Albireo here on the screen, okay, which we're seeing live. It's dynamic, so I can make it shudder and shake. We know things about the stars, but get this. Everything we know about the universe comes to us because we have something that can see the light. Okay? Now, you say, well, what about radio waves? Radio waves are light. They're just light at a longer wavelength. Well, what about X-rays that come from the universe? Well, that's light, okay, but it's a very short wavelength, okay? Gamma rays, X-rays, these are short wavelength radiations, okay? Radio waves, out beyond infrared energy, these are longer wavelengths, all right? And, the visible wavelengths are what we see, from around 380 nanometers out to around 6,500 nanometers, or 650 nanometers. So our eyes are tuned to seeing that. And in fact, our eyes are best at seeing green, Now, I remember one night we talked about the green stars. Do you remember that, Amanda? We talked about stars.
About green stars and the rarity of them?
Yes.
Yes.
Yeah. And, you know, it turns out that there's something called black body radiation. And that is when you have an ideal object radiating energy. It radiates from all the way in the hot blue down to the red, all right? However, the green frequencies are overwhelmed by the yellows and the reds, okay, and the oranges, the yellows, and the blues. It's overwhelmed, and you don't actually see the greens, which is kind of interesting. And so, in our universe, it's almost like, our eyes developed with a special sensitivity to green light. Green is the most sensitive color to your eye. Most people think it's red. It's not. Okay? And our eyes are tuned to green, mostly. Okay? And yet, that's the color in the universe that's least probable. So, is this the universe's way of like sticking its finger in our eye, saying, haha, you can't see the most important stuff out there. You know, I made everything not green, and that's the color I made you see, haha. If our eyes could see different spectrums, different colors that are like the actual spectra, if our eyes could see, for instance, in the infrared or in the ultraviolet, this universe would look very different to us. And I'm going to tell you about an application, if you have an iPhone, that you should go out and get. And this application is really cool because it's it can tell you all about this. Okay? And the application is called SkyGuide. And if you go get it, I don't know how much it costs. It's there's a free version, but I would encourage you to get the actual version. And before you do it, I'm just going to start it up and just make sure I'm not lying to you. 'Cause I don't think I am. I think that this is the one. Oh yeah, I'm not lying. It is actually the one. Good. Yeah. What you can do is you can actually change the light that you're looking in when you're looking at the universe. You can look at the universe suddenly in the infrared, the ultraviolet, the visible, X-ray. So if you had eyes that were sensitive to these different frequencies, you'd actually be able to see them and see how the universe looks. So it's called SkyGuide, and that's on the Apple iPhone. I'm not sure if there's one for the Android, but SkyGuide is really good to actually see the different universe through the different eyes. Now, we've studied the infrared universe with the Spitzer Space Telescope, and Spitzer gave us the first, basically, infrared map of the universe that was really, really detailed. And infrared is heat, right? So heat is electromagnetic radiation. Okay, so electromagnetic radiation is this EM radiation, that kind of thing, is something that we actually utilize to look for planets. The James Webb Telescope, in fact, is going to have primary instrumentation, which is all infrared gear. It's all highly specialized infrared telescopes. So, using the Spitzer, for instance, when a planet passes in front of its star, as it just approaches and about to cross in front of the disk of the star, something amazing happens if the planet has an atmosphere. That atmosphere, that little thin layer of atmosphere, will contaminate the star's spectrum, because that's effectively a cold gas superimposed over very high energy gas and high energy particles that are coming through it. And the particles in that atmosphere will then, the atoms in that atmosphere will absorb some of the energy coming from that star. And that creates a little tiny dark line called an absorption line in the spectrum of the star that wasn't there before. And the James Webb Telescope will be uniquely suited to see these lines. What does that mean? It means that we are going to be able to study the atmospheres of exoplanets and find an oxygen, nitrogen atmosphere if it exists out there. Find, another Earth. I mean, this is going to be a tremendous, absolutely stupendous, next decade in science. And the Webb goes up in 2018. So I'm looking forward to that.
That's incredible. Yes, I'm looking forward to that too.
Yeah, and I realize I'm kind of going on and on and on, and I apologize, but I'm just going to leave you one more time here with this. What's that? Okay, with this view. Actually, that was weird because it looked like I was actually under magnified. That was weird. All right, this is cool. Yeah, this is the one I like so far, because this one actually, you can see all the convolutions in this part of the veil. Supernova.
That's seriously like a piece of art I would want in my room.
Isn't it though?
It's so gorgeous. I cannot get over it.
Yeah, and these are the colors as it is, but you know what's weird? Your eye can't see the colors when there's not enough density of the color in the view, because in a dark sky, well, only your rods are working. The rods are on the edges, the fringes of your eye that are, actually seeing the black and white. And the cones are the color receptors, and those cones, aren't activated by the amount of light that comes through the eyepiece of a telescope. Only if something is very bright can you actually see the colors. That's why when we look at stars in a telescope, we can see the star color, because it's a focused, concentrated amount of light. So once again, in a universal stick in our eye, the universe has designed us so that we can't see the subtle and sensitive color changes in the universe with our eyes. We have to look at them through a technological marvel like a high ISO camera, like this one, for instance. So, that's the thing. And I think it's kind of important to understand that we just don't have the capability to look at the universe with the same eyes as the instrumentation that we've made, and that's okay. We'll figure something out, no doubt in my mind. But someday, who knows? Maybe someday we're going to actually be, we're going to be out there, and we will be in a position to, genetically change our eyes. We might be able to modify how we see with cybernetic implants. I have no doubt that can happen. No doubt, actually. I think, in fact, that's bound to happen, bound to come, before long. And I'm not excited about cybernetic implants, because that means a whole host of things that could be bad. But I do think that we will be in a position to modify ourselves and be able to see in light that we have never been able to see in. I would go for that, actually. I'll tell you a little story. And some of you know this already. A couple of years ago, like I said, when I was coming out of that surgery, I woke up blind because I had like a whole bunch of strokes from the surgery, and so I went through the story before. I won't tell you, but the things I was thinking about while I was lying there blind, okay, were things like, I want to work with the doctors to figure out a way to use different spectral regions, to stimulate my brain, maybe direct access to my brain. I was already figuring if I could communicate with them, I will tell them to be able to, you can go ahead and monkey with my brain, get in there and let's do experiments. Let's pioneer this, And I was thinking I'd have to do that. And here's the weird thing. When I thought that was what I was going to have to do, I was okay with it. I was totally okay with it. I didn't like being blind. I didn't like it at all. But I was okay knowing that, being blind was, I didn't have a choice. I was going to be, that's all there is to it. End of story. Now what are you going to do? Well, I can't do anything. So I will basically work with the doctors to come up with a technique to be able to, see in some way. And I was actually looking forward to it. Which is kind of a crazy thing to think, but I was looking forward to it because I didn't have really anything else to look forward to at that point. So I thought, wow, this would be pretty cool. I can work with the doctors and learn how to see a new way. Luckily, I didn't have to actually follow through with that, or I wouldn't be here tonight with you. Because I don't think my life would have been normal ever again if that was the case, even if I did have this new vision. But that said, I think someday we're going to be able to do this, because as I said this to you before, I don't think that we can think of anything that is actually impossible. I don't think there's anything we can think of that's truly impossible. I think if we can think of it, then it's possible we can do it. Yeah. So with that, I'm going to tell you, and I really appreciate your time tonight coming up here and spending time with me. I just want to say, I want to thank you for coming, and I have a feeling that we're going to have some fun as we move forward here, because the winter sky is approaching. We're going to end up, it's cloudy right now, but we'll see. The winter sky is approaching, and we're going to actually have some fun with the Orion Nebula, and we're going to be looking at the Orion Loop, which is a big loop of nebulosity, nebulous detail, and it's absolutely just incredible, and we're going to go see it. So thanks for coming, guys. And obviously, this music means it's the end of the SkyTour live stream for tonight, August 27th, 28th. Guys, tell your friends about us. Tell your friends about the SkyTour live stream. If you like this, go ahead and hit the bell and get alerts every time we come on. And pass it on to all your friends. Pass it on. Tell them if you liked it. Tell them if you don't like it. If you didn't like what I say, rant at me in the videos. I'll listen. I'll respond. And I will not bump you. I will not kick you out. So, anyway, I hope you enjoyed this. From John Zach Memorial Observatory to you, thank you for coming, and I will talk to you on the next SkyTour live stream. And remember, keep looking up.